Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we jump into section 3.5 in the Big Ideas Math Integrated Math 3 textbook on solving polynomial equations. Now, in the very beginning of this chapter, I had spoken on graphing coming later in the chapter, and I actually anticipated it to be later than this section. I said around maybe 3.6, 3.6, 3.7, 3.8. I can't really remember which one, but 3.5, I'm looking at the very first page of this, and it actually has some of the things regarding graphing that I was talking about. Now we have other things to do. We have to solve polynomial equations. I feel like I've actually done some solving within more of the enriching problems of like section 3.4 and such, but now we get to conclusively do it here. They teach you about it here. We've done some of this stuff before. You have in the past in IM3. Zero product property. You might not know the concept of repeated roots yet, which they're going to talk about, or they say repeated solutions. I call multiplicities. All these other things, but they're going to help us make our graphs, our polynomial graphs. So we'll see what they want as a whole with these things, and we're going to live in solving polynomial equations even in the next section, I do believe. But let's go ahead and get started with it. There's a big key thing that I've hidden that we really need to talk about. We're going to find solutions of polynomial equations and zeros of polynomial functions. This will help us graph them. We're going to use something called the rational root theorem. This is the big one. This is the big thing that's about this section here that's going to be different. You haven't seen it before. You haven't tried it yet. So we'll, we'll play with that. And use the irrational conjugates theorem. We'll talk about that at the time that we get there. You might have heard of conjugates in the past in IM2, but there's a theorem involved with it that we want to make sense of. Repeated solution is a new vocabulary here. You might have heard in the past repeated roots. That'll mean the same thing. What's a repeated root? And I tend to use a different phrase. I tend to use a phrase called multiplicity. Multiplicity. When something is said to have a repeated root, we can also state that it is a multiplicity of a certain amount. Okay, so all these things are interchangeably synonymous in the way that they're phrased. So get ready for those when we talk about them. Previously, we had heard of conjugates before. We know what real numbers are, and roots of an equation are the solutions. They're the x-intercepts, yada, yada. Okay, finding solutions and zeros. You have used the zero product property to solve factorable quadratic equations. You can extend this technique to solve some higher degree polynomial equations. Like I said, I did this for some problems that we had to do. I don't know in what context they were provided, but they said try and find the roots, and that's where they worked out. So we have this one right here, for example. We have 2x cubed, or we've solved the equation, 2x cubed minus 12x squared plus 18x equals 0. Now, the way you generally want to solve these, of higher degree especially, is you want to try and break it down to at least a quadratic and then solve that quadratic by any means necessary. Factoring, completing the square, quadratic formula. I imagine factoring is where they're mostly going to go with these ones. But who knows? They'll probably have some irrational solutions. After all, we're talking about the irrational conjugates theorem, so things can happen. That being said, we have ways of solving cubics or higher degrees based on, is there a common factor, such as this to make it quadratic? Can we factor by grouping, sum and difference of two cubes? There are a lot of scenarios where we can get this solved by factoring even still, and that's our goal. Create a factorization of this to create a product. So first they factor out 2x, the common factor. X squared minus 6x plus 9 factors to x minus 3 quantity squared. We've created a product. 2 times x minus 3 squared is 0. If that's the case, you can use the zero product property. Either 2x equals 0 or x minus 3 squared equals 0. Do the nitty gritty of this, divide by 2 here, take the square root, add 3, x equals 0 or x equals 3. Now we're going to learn some more things in a future section, understanding up to how many solutions you can have or why it makes sense that there are a certain number of solutions here. Here we only have 2 of them. We've learned quadratics have 2 solutions. I'll say right now cubics can have as many as 3 solutions. But the thing about x equals 3 is, x equals 3 is considered to be a repeated solution. A repeated solution of x equals 3 occurs because if you think about factoring this instead of x minus 3 squared, it's really x minus 3 times x minus 3. You know, some people will say either x equals 3 or x equals 3, which sounds kind of weird. And that's where you have what's called a repeated solution, that 3 can be inserted into 2 different factors of this set, whereas 0 can only be inserted into one thing that makes 0 out of it, if you will. And that does something to the graph when you have a repeated solution. Or, as I'm going to tend to say, x equals 3 has a multiplicity of 2. This has a multiplicity of 2, which is just stating the same thing. There are 2 instances of 3 that can kind of be used to solve this thing, to make this thing a true statement. Now, this does affect your graph. Note that the graph of the related function touches the x-axis but doesn't cross the x-axis at the repeated 0, x equals 3, and crosses the x-axis at the 0, x equals 0. So at x equals 3, it bounces off this thing instead. It touches the x-axis. It's a solution. 3 is a solution. Boom, like that. But it doesn't go through like we expect most x-intercepts to do. Instead, it's kind of like a vertex bouncing off of that. It's kind of like it's a quadratic equation there. And that kind of makes sense when you see this squared bit. It behaves like a quadratic there. And I'm sure, listen, I'm going to say, oh, here's their phrase multiplicity. Cool, they say it. I'm scanning around the thing. I'm sure they're going to come up with more general rules for us on how this thing works, but that's how I want to say it. This thing behaves like a quadratic because around 3 it is a quadratic. It's squared. Whereas this thing behaves like a linear, so it crosses through rather linearly. Not truly straight, but like a linear function. So those are your zeros, and there's your polynomial function. Now, this is on a graphing calculator. But if we do know something about these things is it's a cubic, so it's going to have an odd degree and behavior, start in one direction and in the other direction. Because it's a positive cubic, the y equals 2x, etc., it's going to start down and finish up as well. So there are a lot of things about the graph that we should know based off that, and we're going to be sketching some of our own. Now, this concept can be generalized as follows. When a factor x minus k of f of x is raised to an odd power, the graph will cross the x-axis, and when it's raised to an even power, it's going to tangentially touch the x-axis. It's going to bounce off of it. Now, there's more that I'd want to say about like a cubic function. We'll see if we dive into some of those. So there is more that I'm going to say eventually when we hit those problems, because there are different ways you can cross the x-axis. It's not just like this, straight. You could also cross through kind of like a cubic like that. For now, I'm not going to touch those as long as they don't, so we'll see if those surface. That being said, x equals 3 has a multiplicity of 2. You're thinking second degree, you're thinking quadratic, you're thinking vertex and bounce off like that. All right, let's see a second example. Finding zeros of a polynomial function. Find the zeros of f of x equals negative 2x to the fourth plus 16x squared minus 32, then sketch a graph of the function. Same thing as far as the zeros, you're solving for the values of x when y equals 0, trying to find the x-intercepts. So plug it in, set it equal to 0, and solve by factoring, right? We just came off factoring, a lot of factoring we're going to do. Negative 2 is a common factor. This thing behaves in quadratic form. If you factor this correctly, you'll get x squared minus 4 times x squared minus, it's also a perfect square, it's also a perfect square trinomial, but they're going to treat it like this to show the true separation. This factors into x plus 2 times x minus 2 and x plus 2 times x minus 2, and they put the 2x plus 2's together as squared, x minus 2's together as squared. So you have this whole mess of a factorization. Not truly, but it looks like that's a lot of 2's. It does look like a lot of 2's. But think about the zeros that you have on here. One set equal to 0, either x can equal negative 2 or x can equal positive 2, right? Those are your two zeros. But the thing is, each of them are a repeated solution. Each of them have a multiplicity of 2. Because they have a multiplicity of 2, when they touch the x-axis, they don't actually truly cross the x-axis. Instead, they bounce off of the x-axis. So let's read what they say. By analyzing the original function, you can determine the y-intercept. Oh, and I'll talk about the y-intercepts in a bit as well. Is negative 32, but that's because the constant here. I didn't know they were going to touch on that immediately. Because the degree is even and leading coefficients negative, f of x. Oh, I guess they're not talking about the bounce-off function. Let's see. Okay, I guess they're not going to talk about it again, but okay. So negative 2 and positive 2 are the intercepts, but they don't cross through here. They don't cross through. They bounce off of them. That has to do with the multiplicity idea. It'll touch them. It'll touch them. But there are other key features. This is where I wanted to talk about y-intercepts and end behavior. There are other key features that you note. Keep in mind, we're no longer plotting points. We're just coming up with actual features and characteristics of this graph. So we have our x-intercepts. We know that they'll bounce off the x-axis, but how do we know the curve does specifically this? Well, they mentioned it. Negative 32 is the y-intercept. This graph is in standard form, and in standard form, the constant is the y-intercept. If you notice on the previous question, the constant was non-existent. This plus 0, I guess, would be there. So the y-intercept is 0, which makes sense because you have an x-intercept of 0. So there's nothing to speak of on that one. But this y-intercept's negative 32. So again, another point to plot, which means the graph has to touch it. So we know our graph at the very least has to touch this, this, and that, and it has to bounce off of these two. We also know, this is where they're talking about this, the end behavior. The leading coefficient is negative and the degree is even. An even degree will either start up, finish up, or start down, finish down. With a negative leading coefficient, it'll start down, finish down. So we come from the bottom. We touch the x-axis here, bounce off of it. We go through our y-intercept of negative 32. We touch the x-axis again right here, and we come back down. This is a good time for me to mention I don't know how I'm going to choose to draw the graphs for you. Should I attach graph paper, but I have to change my scaling every time? Should I draw generic axes and then rough through it, because that's what I would generally do? I'll probably use the graph paper, but you're going to have to see me change some scaling for things like that. That's a very deep y-intercept. So, guys, we are going to be sketching some graphs. I don't think this is the crux of all the different kinds of graphs we're going to sketch. I think there's more that they're going to have to say. But with that being said, we are going to sketch some graphs. No use of table, just kind of bringing it through where you believe the critical features are supposed to be touched and what kind of end behavior we're supposed to have for what kind of degree. So, 2x intercepts with multiplicity of 2. Y-intercept that it's got to cross through. It starts and finishes down because of the leading coefficient and the even degree. Okay, let's go ahead and move forward. I'll skip those ones. Excuse me. Let me take a sip of water before we buckle up for this one. Okay. Here's a big one, the rational root theorem. I'll get to where they want to state it, but here we go. The solutions of the equation 64x cubed plus 152x squared minus 62x minus 105 equals 0 are negative 5 halves, negative 3/4, and 7/8. Sucky solutions, right? How are we ever going to come up with those? Notice that the numerators, whoa, what just happened? Hold on. Notice that the numerators 5, 3, and 7 of the zeros are factors of the constant term. The constant term, 105, it can divide by a bunch of other numbers, but it can divide by 5, it can divide by 3, and it can divide by 7. Also notice the denominators, 2, 4, and 8, are factors of the leading coefficient, 64. Once again, 64 can divide by many other numbers, but among them are 2, 4, and 8. These observations are generalized by the rational root theorem. Now, what they were talking about were these constants up here, 5, 3, and 7, and the numbers down here of 2, 4, and 8. Some may be negative, some positive, but we'll get into that. The rational root theorem states this. If f of x equals a polynomial, and that has integer coefficients, these are integer coefficients, that's met, then every rational solution of f of x equals 0 has the following form. P over Q. P represents the factors of your constant term, this guy, and Q represents factors of your leading coefficient, this guy. The possible list of solutions, of rational solutions, exists within that form. You divide all of your factors of your constant term by all of your factors of your leading coefficient. All of those are possible roots for which we can test to see which of these are true solutions of our thing. Because I've mentioned this before, before I move forward. Let's look at this problem again. This problem is so big, so rambunctious, there might not be some other way you know how to solve. I don't even know if there's a GCF on this one. But you can't factor it by grouping, and they didn't give you any solutions. And let's say we couldn't use the graphing calculator to find where it crosses. And even if you did, these numbers aren't perfect to determine anything anyway. What would you do in that situation? Well, we would find a rational root using the rational root theorem, test it out, use synthetic division to turn it into a quadratic, and then solve from there. But we first have to find a rational root. That's the goal. We're going to list P's and Q's, P's over Q's of our set. We're going to come up with which ones work. Some will work, maybe none will work. It depends on if it has any rational roots. Some may have multiplicities, means it may work more than once. But we'll see when we get there. Let's see what examples they have. We're going to have to do a lot of this. This may be one of those longer videos. The rational root theorem can be a starting point for finding solutions of polynomial equations. However, the theorem lists only possible solutions. In order to find the actual solutions, you must test values from the list of possible solutions. We've practiced what it means to do tests. We can either plug them into the function, which I'm going to do, using a graphing calculator. You can either plug them into the function and see when it equals 0, or use synthetic division on it, see if you get a 0 remainder. Now, here's what I'm going to plan on doing. I'm going to plan on plugging them into a graphing calculator and see when I get 0. When I do, I'm going to use synthetic division on that root and start the factoring process. All right, example 3, using the rational root theorem. Find all real solutions of x cubed minus 8x squared plus 11x plus 20 equals 0. Now, straight up, when I see this, I can tell you right now, you cannot factor this by grouping. So rational root theorem must be the way to go. By the way, before I move forward on this, I'm going to state, after this section, there is a video I've attached a couple times called Factoring Factory. And I've always stated that there are some kinds of questions in IM3 that you could, there are some kinds of questions you couldn't see the answer on there until we learn more in IM3. The rational root theorem, I think, is the last kind of thing you're going to have to know. You now know sums and differences of cubes. You now know quadratic form. You know factoring by grouping. Rational root theorem is the last thing to use. So if you want to practice factoring factory, that packet, I'll attach it down below as one of the additional resources. It's just a factoring practice thing. And rational root theorem questions will pop up quite often. I'll do P's over Q's kind of testing on those ones. Anyway, I just wanted to bring that up. Okay, here's the solution. The polynomial is not easily factorable. As I've stated, there's no factoring by grouping or anything like that. We're going to begin by using the rational root theorem. We are going to come up with possible rational roots of this set. We're going to test one until we find one that is a 0 of the function, and then we will use synthetic division to divide this out. So what are the possible rational solutions? The leading coefficient is 1, and the only possible factor of 1 is 1, right? 1 can only be made from 1 times 1, or negative 1 times negative 1. And I want to bring that up as well. Keep in mind that there are negative possibilities on here. I might write this differently than they do, but the constant term is 20. Those are our p-values. Factors of 20 are 1, 2, 4, 5, 10, and 20. Those are possible rational. Those are possible those factors of 20 can exist as our possible rational solutions. The possible rational solutions divide all of your constant terms, factors, by all of your leading coefficients, factors. So one, you know what's missing on here? I just noticed. You know why there's weird spacing? This book does this all the time for some reason digitally. These should all show plus or minuses. Plus or minus, plus or minus, plus or minus, plus or minus, etc. That's where I was saying negatives should also count. They intended to put plus or minuses on there. For some reason, the digital version of the book misses it. Your textbook should have it in print. Anyway, 1 over 1 is 1, 2 over 1 is 1, things like that. So keep in mind. All the possible solutions, there's 1 and negative 1, 2 and negative 2, 4 and negative 4, 5 and negative 5, 10 and negative 10, 20 and negative 20. Not all of them will clearly be solutions. As many as 3 can only be solutions. One of them must be for a cubic. There's something that I know about that you wouldn't. So they're going to test values until it works. Now, they are going to test solutions using synthetic division until a solution's found. Unless they force that on me, guys, I'm going to use a graphing calculator, and I will show you for this exact problem how I'm going to use the graphing calculator. It's not that synthetic division's bad, it's that it takes time that I don't necessarily need to use if I have a graphing calculator, and I will do synthetic division on it after I find a 0. Now, the first test they do is 1 by synthetic division, and they get a remainder of 24. 24 is not 0, therefore 1 is not one of the rational solutions of the set. It needs to be 0. Then they go and try negative 1. Remember, plus or minus 1 is among them, along with all these. Then they try negative 1. So they do negative 1 on this, and then they end up getting the f of negative 1 is 0. Therefore, negative 1 is one of the rational solutions of this function. That also means, by the way, in factored form, that x plus 1 is a factor of this polynomial. So they technically divided x plus 1 out, and they got this remaining quadratic. It's the same kind of thing we were doing before, only we have to test for 1 to find which one's a 0. Now, before I move forward on the rest of the problem, let me do this with the graphing calculator as well to show you what I would do in this case. On the graphing calculator, I would type in the original function, x cubed. Now, I'm fine doing 1 and negative 1 and things like that by hand, and I've showed you before that when you plug in 1 into this, 1 cubed is 1, minus 8 times 1 squared is minus 8. Those are pretty easy to do, but if you're doing it in one fell swoop and want to test everything under the sun, you can do it like this. Make your equation. In your table set, ask for very specific inputs that you're going to use. Go to your table and plug in numbers. I can plug in 1, 24 was that value. We saw that. I can plug in negative 1, you get 0, right? You can keep trying to plug in some numbers. For instance, if you tried 2 and negative 2, I'm not going to spoil ones that are answers. You can see that these were also not zeros. There are only some possible rational zeros. Negative 1, I should say, is a guaranteed one. Once I determine that negative 1 is one of them, I'm then going to use synthetic division on it the exact same way that they did. But I'm not going to, spend time doing it on ones that don't work because that'll just add up time. I immediately tested in my graphing calculator that 1 didn't work, and then I'll move on from there. So I hope that's okay. Unless they force it on me, I'm not necessarily going to do that. Anyway, we're going to keep factoring this guy. Remember, x plus 1 is one of the factors, so you factored that out, and you're left with x squared minus 9x plus 20. And then you factor that down and you solve the rest of the way. Not unlike what we've done before. I believe we've even done solutions of them. Even in zero product property, otherwise, whatever. We've done solutions of these things. At the very least, we've factored them. When we factor them, set them equal to 0, we can now solve, and your solutions are negative 1, 4, and 5. So apparently, if I plugged in 4 or 5 in my calculator, I also would have gotten zeros out of that. Plug in, whoa, what's that? Plug in 4 into there, you get 0. Plug in 5 in there, you get 0. Those are the only 3 in these cases that'll be 0. This cubic only has 3 solutions. Nothing else would have worked. 10 or negative 10, 20 or negative, nope, none of those. So these are the only 3. Now, can you use the graphing calculator to find all 3 and be done with it? I suppose. The goal is, the only thing I'm doing is I'm saving a little bit of time by finding one of the solutions, and then I'm following the process the rest of the way. I promise you. What I don't want to do is spend time going plus minus 1, plus minus 2, plus minus 4. Oh, those don't work. And eventually there will be problems that have fractions with them, and I don't want to spend time testing all those fractions. I want to find one of them, get it right, and then move on from there so I can find the rest. I won't use the calculator for all of them. Okay, in example 3, the leading coefficient of the polynomial is 1. When the leading coefficient is not 1, the list of possible rational solutions or zeros can increase dramatically. Yes, 2-fold, 10-fold, whatever it is. In such cases, the search can be shortened by using a graph. More than that, guys, so I must have jumped the gun by saying graphing calculator because now they're using it. They're going to use the graph. I might go and use the table still just to kind of give you the idea because I don't want to spoil all my solutions, so they're kind of giving what they all are right now. But here are the possible rational solutions of this function for this example. Notice your constant is 12, so your factors of 12 are 1, 2, 3, 4, 6, and 12. So those are numbers that can go on top right here. And then on bottom are your factors of 10, which are 1, 2, 5, and 10. So notice, divide 1, 2, 3, 4, 6, and 12 by 1, divide them by 2, divide them by 5, and divide them by 10. Now, if you'll notice, there are some numbers that you're like, wait a minute, where's 2 over 10? Wait a minute, where is 4 over 2? Well, remember, 2 over 10 reduces to 1/5, and 1/5 is written right there. 4 over 2 is 2, so that's written right there. There are some parts that thankfully reduce, so it's not quite as long as you'd think that it would be, but they can get still pretty long. That's a lot of numbers to test, and that's why they're saying don't use synthetic division on all of them until they work. In fact, if you tried any of the integers, apparently none of the integers would have worked if you look at the solution. They say choose reasonable values from the list above to test using the graph. So they're doing kind of an alternative take on what I was saying by using a table. I'm kind of doing my way versus them doing their way. The bottom line is sometimes you can use a graphing calculator. I'm pretty much always going to use the graphing calculator if 1 or -1 doesn't work. I can do 1, -1 in my head. I can do a lot of them in my head. I just don't want to spend a lot of time doing it if I don't have to. See, if I did all of these tests, otherwise it would be a problem. So let's check that one out. 10x to the 4th. 10x to the 4th minus 11x cubed. Minus 42x squared. Plus 7x plus 12. So they went on the let's use the graph and show where it's crossing through, which is, it's fine. And they said test reasonably around what you have. Obviously, their window range is different from mine because my graph looks strange compared to theirs. But if you remember some of the list here, right, we're going to try and find, I keep doing that, I'm sorry. We're going to try and bounce around and find which of these are what we're supposed to look for. As you notice, -1/2 is one of the solutions on there. Let's go and find -1/2 from our graphing calculator there. If I go left, you can see, I guess I do have to change my window range. Let's do this. I want to make it look a little more pleasant to us. Let's see what this does. A little bit more of a curve. There we go. There's a little more curve action to this thing. It's not perfect with it, but still. You can see that when I go over here, I'm guesstimating that, hey, there's that -1/2 about that should be working. I don't think that's an exact way that we should be talking about it, though. That's where I'm still going to be using the table. So I do have a table here. Keep in mind, you can plug in all these values and determine that, none of these are actually going to work if I tried to plug in, again, 1 or negative. I guess that's not a negative symbol. -1, 2 or -2, -2 or 2, things like that. In fact, the larger they end up getting as I try like 6 and -6, you can see that they're just getting larger and farther away. At that point, I give up probably on integers and say they might have to be fractions to be those answers because this is where you're seeing the end behavior of the graph. So it's at that point I try something like, all right, let's try 1/2. No, let's try -1/2. And boom, hey, there's one of the zeros. -1/2 is one of the zeros. Now, if you go to their problem, They found a couple of them. They said test the values using synthetic division until a zero is found. Keep in mind, negative 1/2 was one of the zeros. We already found it. So you still have to use synthetic division on this, or long division. And there's reason why you might want to use long division for this. I'm going to talk about that in a moment. But it depends on who you are. But negative 1/2 does work. Use synthetic division on that. You get this polynomial. Now, when you factor this thing out, right, x plus 1/2 came out. This isn't how we tend to see these things, and I'm going to show you what happens as a result of this. This 10x cubed minus 16x squared minus 34x plus 24, that has a common factor of 2 that we can pull out of there. They pull the 2 out of there, and we distribute it into these ones, right? We create it for what the negative 1/2 root was actually probably from. Remember, these were integer coefficients. So integer coefficients means that you probably had all integer values here. 2 times 1/2 is 1, 2 times x is 2x. 2x plus 1 is a common kind of factorization that you can see. Remember, this would give you x equals negative 1/2 when you solve using zero product property. The fraction answers come from dividing by whatever this leading coefficient is. So we pull the 2 out from whatever this is, and we let it go into here. That's why I said long division may be the way to go, because if you know that negative 1/2 is one of your roots, again, x equals negative 1/2, that means that x plus 1/2 equals 0. Multiply everything by 2. 2x plus 1 equals 0. So you can divide by 2x plus 1 using long division instead of using negative 1/2 as your synthetic. I'm likely going to do this more often than not, if not all the time. These numbers should come out clean. Half of 10 is negative is 5, and things like that. So that's not too bad. Anyway, you get a cubic here. This cubic still, however, is not fully factored. I still can't factor by grouping. So now we have a new function for which we still have to keep breaking it down. This problem takes a while. Now, there's nothing of old that doesn't exist as your possible rational roots. These are ones to still test out of. This list might have diminished a little bit because now this is just a 5 and this is just a 12 instead of being what it was before, a 10 and a 12. So now you have a little bit less to work off of. So these are your possible rational roots to choose from. I want to remind you, although you saw the graph of this last problem, that technically negative 1/2 should still qualify as another possible rational root for this. Remember, you can have repeated solutions. You can always test negative 1/2 again, but ones that didn't work before won't work this time, so it's best to ignore those. Anyway, the graph shows that 3/5 may be a 0, so you get to synthetic division, you break it down again, you do the same things you did before. You end up getting this new polynomial, factor out the GCF and put it into this guy instead, and you get this new factorization again. And now you have 2x plus 1 and 5x minus 3 as factors. The final factorization here is x squared minus x minus 4. Now we're at a quadratic. So rational roots, here's the thing. Rational roots here aren't the things you might necessarily want to test anymore. Now solve quadratics the way you do. And keep in mind, these roots also might not necessarily be rational. And they're not. This isn't factorable. So how do you solve? My go-to is the same as the book, quadratic formula. X squared minus x minus 4 equals 0. We go to x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You end up getting 1 plus or minus root 17 all over 2. There are 4 different solutions. These two were not rational solutions. That negative 1.56 and 2.56, those weren't actually negative 2.5 and 1.5 and whatever. Negative 3 halves, although it was on this list, negative 3 halves was not actually one of them. 5 halves, I thought I saw 5 halves on here. Oh, maybe not. Not 5 halves. Anyway, those aren't on this list. You solve them through these means right here. Let me pause for a sec, clear my throat. Okay, so yeah, they throw you into the deep end for this problem here. It's quite a lot to do, and that means there's quite a lot for us to do. So keep that in mind for each problem. There are tests that we're going to do to find a rational root. Then you synthetic division, pull it out, and keep factoring as we need to. Whether we got to use rational root theorem again, whether we can now factor by grouping, sum or difference of two cubes, find other GCFs, which you should start by finding. Whether you can just factor the quadratic or solve the quadratic using your own means. That's what we're going to do when we get to those problems. Okay, the irrational conjugates theorem. In example 4, the previous example, notice the irrational zeros are conjugates of the form a plus root b and a minus root b. Remember, conjugates appear in these solutions because, or not they appear in there because, when you have all rational coefficients and you have irrational solutions, such as these ones, they must come in conjugate form. That's how they cancel each other out. That's how they work. Now, the irrational conjugates theorem states that if f's a polynomial function with rational coefficients, then let these be rational numbers such that root b is irrational. If a plus root b is a 0, then a minus root b must also be a 0. They must always appear in conjugate pairs. Okay, so let's look at the example using zeros to write a polynomial function. They say write a polynomial function f of least degree, meaning the smallest degree that you possibly can, that has rational coefficients, a leading coefficient of 1, and the zeros 3 and 2 plus root 5. Now, because they need to have rational coefficients and because you have an irrational solution as this one, its conjugate also must be one of them. That's what they're saying. Because 2 plus root 5 is a 0, 2 minus root 5 also must be a 0. So those are going to be among them. Now, if you've noticed from solutions that I've done this in the past, I'll say, hey, x equals 3 is a solution. So x minus 3 equals 0 means x minus 3 is one of your factors. And hey, x, plus, or x, sorry, let me do that again, equals 0. And you see that one right here. Now, these ones also appear in that form. You can say something like, hey, if x equals 2 plus root 5 is a solution, then x, you subtract this over, minus 2 plus root 5 equals 0 means x minus 2 plus root 5 is a factor. And there's that one. And then the other conjugate is there as well. Now, they do a regrouping of terms. There's a reason for this. It creates a difference of two squares this way. If you use the associative property and state that instead of x minus parentheses 2 plus root 5, you distribute the negative, and then you go ahead and take the parentheses around these guys here. Again, distribute the negative. Then you have a difference of two squares. You have a minus b times a plus b, which becomes a squared minus b squared. It's just kind of a way of cleaning that up faster instead of multiplying two trinomials together. There are other ways you can do it from this stage right here. It's going to take a little bit. I'll do it the same way that the book has it here. Anyway, you keep distributing. You keep distributing. Notice that they also said it needs a leading coefficient of 1. That means I place a 1 right here, and 1 times anything is just itself. So they expand this thing out. They combine like terms. Now they multiply this thing out, and they end up getting this polynomial. So I'm not going to spend the time doing all the little parts that they have, but that's how they're doing the simplification process, starting by creating the factored form of this polynomial and getting the fastest way to do the expansion of the polynomial and combining like terms. They do a double check with that. I'm going to leave it be, but they try and plug in their numbers like 3 and stuff, make sure they get a 0 out of that. I'm going to leave that. There's a lot of work that you'd have to do otherwise. I'm not down. Okay, guys, that is it for the lecture, which is, again, a long one. That is just how these things go. We're going to go ahead and take a look at the vocabulary and core concept check. These first two questions. Complete the sentence. If a polynomial function f has integer coefficients, then every rational solution of f of x equals 0 has the form p over q, where p is a factor of the constant term, and q is a factor of the leading coefficient. So you test all factors of p, all factors of q, and create p's over q's as possible rational ones. Test them until you find a 0. Use synthetic division. Keep moving forward. Different word, same question. Which is different? Find both answers. Find the y-intercept of the graph of y equals x cubed, Well, that y-intercept is 2. You set x equal to 0 for that. Find all the real solutions of this. This would be different. These are values of x when y equals 0. This is a value of y when x equals 0. That's different. Find the x-intercepts. That would be the same as this one right here. So this is different with it. Find all real zeros would also be this as well. That's where you set y equal to 0 among any of these, or when set equal to 0, you solve for x, finding x-intercepts where they cross there. This is finding values of y when x equals 0, where it crosses the y-axis. That's the different one. All right, guys, I'm going to go ahead and get started on the problem set. We are doing up to problem number 65, quite a bit, especially if we have to use the rational root theorem for a lot of them. But first, we're going to start on things before that, probably things with graphing as well. So let's go ahead and get started. Now it's time to see this line paper, because before I was popping up over and over, my bad. I have different hotkeys and messed up which one I was doing. All right, let's start with numbers 3 through 12 and solving the equation. Basically, factoring, or set it equal to 0, factor using zero product property. Factor and solve using zero product property. So number 3, we have z cubed minus z squared minus 12z equals 0. I see a common factor of z that can come out of here. And then this quadratic can factor down to z minus 4 times z plus 3. This is zero product property in use now. If z times this equals 0, then z equals 0. if this times z minus 4 equals 0, then z minus 4 equals 0, so z equals 4. And if z plus 3 equals 0, then z equals negative 3. A lot of times I'm just going to do the whole, hey, just flip the sign, and it depends on what we're dealing with, so you'll see me go a lot faster on those as we feel more comfortable as a whole. All right, there's number 3. Let's go on to number 4. Also a common factor one. We have a cubed minus 4a squared plus 4a. Oh, I see what's going on. Equals 0. Sorry, let's see. Factor out an a, and we have a squared minus 4a plus 4 equals 0. Now, you may notice this is a perfect square trinomial. The two numbers that multiply to 4 and add to negative 4 are negative 2 and negative 2. So I want to get right into that right now. This factors into a minus 2 quantity squared. Right? So a can either equal 0 or a can equal 2. Now, when a equals 2, I want to note, because it'll be important when we do graphs with them, this is a repeated root. This has a multiplicity of 2. That'll be important again when we do those graphs. You'll see it bounce off of that. I want to say x-intercept, but I guess a-intercept. It would bounce off of that intercept instead of going through it. So that's something that we're going to have to know when we do the graphs. Number 5. 2x to the 4th minus 4x cubed equals negative 2x squared. Now, you need to set this equal to 0 before you do any of the solving using zero product property. It can't be zero product property if it's not equal to 0. Now, what I'd recommend in a problem like this, besides the x common factors, is also factoring out that 2. Factor out all of 2x squared, and now you have 1x squared minus 2x plus 1. Now, before we move, it's not yet a full product. It's a product, but this thing still has some more to go. So this is also a, perfect square trinomial. This factors into x minus 1 quantity squared. So you got yet another one of those. Now, if 2x squared equals 0, then divide by 2 and take the square root of both sides, you get x equals 0. That's one of your solutions. And x squared, same thing. I kind of showed it on the last one. I probably tipped my hand. Take the square root of both sides and you add 1, you get x equals 1. Those are your two solutions. Now again, we're going to learn more in the next section on this, but this is a quartic function by leading term, which means you can have up to 4 solutions. This only had 2. The idea of these two solutions are they each have a multiplicity of 2. This has a multiplicity of 2, this has a multiplicity of 2. Therefore, that's how the 4 solutions are explained away. So, is this a requirement for you to write here on these problems? I don't know. Probably not. But again, important for graphs. Number 6. V cubed. Why are these just x's? V cubed minus 2v squared minus 16v equals negative 32. V's are starting to look like u's. Add the 32 over. I see no such common factor in this problem, but I do see, prospects for factoring by grouping. We're not doing rational root theorem yet. So I can pair off these two, find the common factor among the first two terms, which is v squared. You're left with v minus 2. Factor in negative 16 out of these next two terms, you also get v minus 2. V minus 2 is a common factor out of those guys, which pulls out, and you have v squared minus 16 from the other two. And v squared minus 16 is a difference of two squares that factors into v minus 4 times v plus 4. There's still the v minus 2. There are your 3 factors set equal to 0. If we want to solve this, we're going to get v equals 4, v equals negative 4, and v equals positive 2. Okay. Number 7. 5w cubed equals 50w. Again, really refrain from doing any division on these. Instead, do factorization. Factor them out. You definitely don't want to divide out solutions. If I divided by 5, no biggie. If I divide by w, that's a biggie. So instead, I'd rather do the factorization of this. 5w cubed minus 50w equals 0. Factor out a 5w from both terms as it's a common factor, and you get w squared minus 25. You guys notice the difference of two squares here? This is where they just got to call attention to, right? W minus 5 times W plus 5 comes out there. Now, 5W equals 0 means you can divide by 5 and you get W equals 0. There's one of them. W equals positive 5 and negative 5 are the other two based off the difference of two squares that we had before. Number 8 looks like more of the same. 9 9m to the 5th equals 27m cubed. I subtract 27m cubed over, set it equal to 0. Factor 9m cubed out, and I'm left with m squared minus 3. This is not a difference of two squares, but this is a product, so we can do the whole either this equals 0 or this equals 0 thing. So I still got to solve the ones here, right? After all, I'm going to solve the ones on this other side. Now, the ones on this side, you divide by m and you take the cube root of both sides. The only value you can plug in for here is 0. That's going to work. But I want to talk about that one more. This one actually has a multiplicity of 3. Now, I don't know if this section intends on having us graph polynomials with a multiplicity of 3 because they won't bounce off the x-axis. They'll go through it, but not like this. Instead, they'll go like this. They'll go like that. I don't know if they intend on having us do that. I'm just making mention of it the same way I did for the other ones. This one over here, we have to add 3 to both sides if you want to solve by using square roots, and take the square root of both sides. You get m equals plus or minus square root of 3. These are the other two solutions. Remember, positive square root of 3 is a solution, negative square root of 3 is a solution. Those solutions are not rational, but they are real, and they do exist in this set. So there are ways you're going to have to solve quadratics. We got factored as much as possible. Zero product property is in use. There's just more to do in the set that we had. We're not going to say, well, we're not going to factor more from that. That's what we do. Anyway, this was a 5th degree polynomial. So m equals 0, 0, 0. Root 3 and negative root 3 are the 5 solutions that are there. Number 9. I'm probably over speaking on that part only because that's a big, heavy part about next section, but I'm reminding you why I'm writing multiplicities of 3. 2c to the 4th minus 6c cubed equals 12c squared minus 36c. Let's bring these all on one side of the equation. Set it equal to 0. Make sure it's in standard form, by the way. It seems like they're really setting it up for you to still be in standard form. All's good there. All right, what's common factor you see? I can pull out a 2 and a c. Here I'm left with c cubed minus 3c squared minus 6c plus 18. And this looks to be factorable by grouping, so let's proceed on with that. If I factor out a c squared from the first two terms, I'm left with c minus 3. If I factor out a 6 from these two terms, I'm left with c minus 3. Perfect. Now, this is 2c times the next two things they factor out as, right? c minus 3 factors out from these two terms, and you're left with c squared minus 6 from these two terms. Still set equal to 0. The whole goal is solving using zero product property. If there are two that you think you can solve pretty immediately, it's this one, c equals 0, and c equals 3 on this one. This one might take a little bit more. It cannot factor more. It is not a difference of two squares since 6 isn't a perfect square. So c squared minus 6 equals 0. Let's solve using square roots, add 6 to both sides, and take the square root of both sides. C equals plus or minus 6. As a quartic, I see 1, 2, 3, 4 solutions, and that's what I anticipated. Number 10. I like the diversity of problems they have. This is a very good problem set, like not just from this section. They've come up with very good problem sets diversifying all the different kinds of factorizations you had. Yay book. They've been doing great. P to the 4th plus 40 equals 14p squared. I'm going to subtract 14p squared from both sides. There is no common factor. However, when set equal to 0, we can still solve by factoring. This is in quadratic form, something we learned in the last section on 3-4. Treat these basically, instead of just p minus and things like that, it's p squared minus, right? P squared times p squared is p to the 4th. These will combine to become p squareds, all that jazz. So what two numbers multiply to 40 and add to negative 14? Negative 10 and negative 4. Now, p squared minus 10 is not a difference of two squares. However, p squared minus 4 is. This factors into p minus 2 times p plus 2. Now, it's not unallowed, guys. It's not unallowed to solve. Here, let me actually do this. It's not unallowed to solve for these both the same way, meaning with p squared minus 10 equals 0, you have to add 10 to both sides and take the square root of both sides, right? It's not unallowed to do that right here as well. I can say p squared minus 4 equals 0 and solve however I want. I can solve using square roots. I can solve using quadratic formula. But the bottom line is this one was also factorable. So I will solve by factoring. But when I take the square root here, I get plus or minus 2. So you can do that. But if they ever ask you to factor completely, you have to know that you got to get it factored into here. If you want to ensure yourself your two solutions, I recommend you factoring this way. That kind of thing. So anyway, here's where you get your p equals 2 and p equals negative 2. Remember, me writing plus or minus 2 is another version of that. It's just this one wasn't factorable. So here we got to do what we just did above, add 10 and divide by, or take the square root of both sides. Like that. So 1, 2, 3, 4 solutions from this quartic is all good and dandy. So either or when it comes to one of those, but I'm going to always factor difference of two squares and things like that. Just make sure you really work on that. It's especially important, and we haven't run into it yet, if we have a sum or difference of two cubes that we do it that way. Don't just be taking the cube root of both sides. There's more to be doing on those. Number 11. Now, I don't know if we're going to run into them. I don't know to anticipate it or not. 12n squared plus 48n equals negative n cubed minus 64. I'd love to get everything on one side of the equation, but most importantly, I'd love to get this term positive, my leading term. The cubic. This is a cubic. Add n cubed to this side. Get it in standard form, so I still want my plus 12n squared plus 48n. And add that 64. Okay, I believe I spoke too soon on saying they wouldn't introduce rational root theorem here yet. This is not factorable by grouping. If you want me to show you that it's not. This is me knowing things. Okay, this is just me knowing things. If you attempted to factor by grouping, you'd get n squared as a common factor of these two with n plus 12. And you can factor as much as 16 out of here, and you'll be left with 3n plus 4. Guys, these are not the same. N plus 12 and 3n plus 4 are not the same. You cannot factor by grouping. So we need to solve using other means. In this case, the other means entails rational root theorem. We have to find a possible rational root that exists inside of here. So we have to choose p's over q's, possible rational roots that will work out of here, so we can then use synthetic division to get what it is that we need out of it. Okay, so it's going to take a little bit of work. We need some work on this thing. Unless I wrote the problem wrong. I think I wrote it right. I just didn't expect this early. Possible factors of 64, guys, are, I'm going to write plus or minus, and I'm going to write it as a list to begin with. Then we can treat them as fractions. 1, 2, 4, 8. Is the next one 16? 16, 32, 64. Did I leave anything out? I felt like there were a lot more than that. 64. Factors of 1 are just 1. So divide these by 1. So here are all the possible rational roots here. Divide these by 1, you get plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32, plus or minus 64. There are 1, 2, 3, 4, 5, 6, 7 times 2, 14 different possible rational solutions here. And we don't know if all of them are rational solutions. I know there's at least one. I don't know which one yet. We got to test it out. The thing about the test, though, which is interesting enough, and I spoke on this once in, I think, section 3.4, I might have spoke on it. Because all of these are pluses, it would actually be impossible to have a positive rational solution here. Imagine, plug in 1. This would be a positive plus a positive plus a positive plus a positive. It's impossible to get 0 from that. So the only ones that are possible are negatives. Now I'll try negative 1 on my own, see how it works out. We get negative 1 plus 12 minus 48 plus 64. That's 76 minus 49. That's not 0. So negative 1 didn't work. This is, guys, where even if negative 2 might be it, I'm going to go to the graphing calculator and kind of get the rest of them down. I'm going to clear out the one that we did from the lecture. Let's go to 1n cubed. I got to use x. Plus 12n squared. Plus 48x. Or n, whatever. Plus 64. And what we're going to do is just make sure that you're in ask mode on the table, and you're going to substitute your own values here from the rational roots. The possible ones I'm going to try are negative 1, I said wouldn't work. Negative 2, didn't work. Negative 3, or negative 4, there's a rational root. So let's divide out, let's factor out an x plus 4. Let's use synthetic division with x plus 4, meaning we actually get to just choose negative 4 as that root. So I'm going to say negative 4 is a rational root. Normally I wouldn't write that. I'm just kind of providing for you what we're going to do next with this. As in, oh, you know what I'll normally write is if it's an actual polynomial thing, I'll say like if it's an f of x, I'd say f of -4 equals 0, that kind of thing. I'll say, okay, that's one of them. But what we do off of that is now synthetic division. I'm going to use -4 as that root. My coefficients are 1, 12, 48, and 64. Now, the thing is, we're not testing to see if we get a 0 remainder. We know we will. We're doing division so we can reduce this polynomial. It was a cubic. I need to make it a quadratic. I need to solve the rest of these. So use synthetic division as you've learned how to do so. Here's that 0 remainder. That's a good reminder of what this thing is. Now we're left with an n squared plus 8n plus 16 as the other factorization. Keep in mind if -4 is one of your roots, then n plus 4 is the factor. The other factor among this is n squared plus 8n plus 16. So, interesting. So, with this one here, n squared plus 8n plus 16 actually factors into n plus 4 quantity squared, which is really interesting on this because that means this is all n plus 4 quantity cubed. N plus 4 quantity cubed equals 0. The only solution that's possible for this thing is n equals -4. Which is very interesting to state because that means none of the other rational solutions would have worked, right? And I mentioned this in the lecture. I said just because -4 is a rational root that you found once doesn't mean it can't be again. One that couldn't be before can't be later, as this thing factored into here, but n equals -4 has a multiplicity. What's it? Multiplicity of 3. Now, if I don't think I would have noticed for myself, but if I paid close enough attention, maybe I would have been able to notice that this is n plus 4 cubed, because as you know, this is just me doing some extra fluff work. As you know, n plus 4 cubed should equal 1 times n cubed plus 3 times n squared times 4 plus 3 times n times 4 squared. I don't know how I'm choosing when to write parentheses and when not to plus 1 times 4 cubed, which would be n cubed plus 3 times 4 is 12n squared plus 16 times 3 is 48n plus 4 cubed is 64 times 1 is 64. So we get that out. Okay, I guess that would have been that. I have no reason to know that would have been a perfect cube there. So we had to use rational root theorem to kind of deduce that, and there it is. Okay, number 12. Maybe this is also rational root theorem now that I was caught off guard with that previous one. Y cubed minus 27 equals 9y squared minus 27y. My y cubed here is already positive, so let's subtract the 9y squared over. Let's add 27y over, and we got minus 27 here equals 0. This also can't factor by grouping. Just take my word for it unless you want to test it for yourself. My guess suddenly on this one, based off the last problem, my guess is the answer is going to be y minus 3 quantity cubed equals 0, therefore y equals 3 would be the answer. Meaning this would be the factorization. Maybe it's a perfect cube of that. It kind of looks like it probably is. But we don't know that at this point, right? We don't know that at this point. So I'm just going to leave that to the side, sidebar. Let's go ahead and try this for ourselves. Rational root theorem, something we got to practice anyway. So let's try our p's over q's of this guy here. Factors of 27 are 1, 3, 9, and 27. Factors of 1 are just 1 and -1. So your possible p's over q's that we're going to be testing are plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27. Unlike the previous question, because there's a combination of positives and negatives here, positive solutions can possibly work, so you want to test those ones. Now, I'm anticipating that 3 is going to work, and I really anticipate 3 is the only one that's going to work here. So I'm going to go to my calculator again. I'm going to type in this function. I don't know if this is what they expected you to do here. I felt like rational root theorem was supposed to just come later in this, and I don't really know what they expect you to know here. I had no reason to believe that that would have been a perfect cube. You can't factor by grouping, so it's just one of those, I guess you got to know. I guess you got to know. So anyway, that being said, let's keep going on this. 9x squared plus 27x minus 27. Okay. Give me 1 second. Okay. So let's ask to plug in some values here. Let's go with there's 1, negative 1, 3, negative, oh, look, we got a 0 on there at 3. Okay, so this was the expectation, right? Kind of expected this thing to happen. So let's go back. 3 is a root. As you can tell, 3 is a root. Because 3 is a root, now we can use synthetic division on our polynomial with coefficients of 1, negative 9, 27, and negative 27. There's got to be another way to go about this problem stuff. I don't believe the book would start using rational root theorem this early, not the book, this section, because it's not its own section of problems. There must be some form of, I mean, it must be factorable because it's factorable. Like, if that makes sense. There must be something else that we can discover with this to make it work. And I'm keen on looking for it. I'm going to discover it for you guys in a bit. It must be here. Anyway, so y minus 3 is a factor. Y minus 3 is a factor. And this guy here is y squared minus 6y plus 9. It's all set equal to 0. This factors into y minus 3 quantity squared. And much like the other problem, this can now merge into y minus 3 quantity cubed. And you just saw it on the other thing that I wrote up above. That would mean y equals 3 for all sets, right? Take the cube root, add 3 to both sides. Y equals 3 is your one and only solution's got a multiplicity of 3. Not because of knowledge that, like, oh, I could totally tell that this was a perfect cube kind of thing. But there's something, there's no way, because we're not doing rational root theorem yet. So, listen, what we did is fine. And we're going to do a lot more of this later. Maybe I don't have to teach it as much later now. But these two problems, there's no way that those perfect cubes can't be discovered with something else. You know what is interesting about this, and I'm actually willing to test this theory on them, is the way they wrote out the problem initially, and this isn't something I'd see for myself, and I don't know if it works, but that's a difference of 2 cubes. This is, it's technically a sum of 2 cubes because you can factor a negative out of there. Let me play with these problems again, guys. I'm going to explore a little bit here. Let's go back to number 11. I'm going to go back to number 11. I'm going to rewrite it one more time and see if I can use a different form of factoring by grouping on this thing. So 12n squared, maybe they were telling us something by putting these things together specifically. Now, like I stated, I'd rather factor out a negative from this thing and get n cubed plus 64. And that's the beginning of my factorization there, because that is a sum of 2 cubes. And here's 12n squared plus 48n. Okay, this does have a common factor of 12n, and the reason I bring this up is because this does have n plus 4 as a factorization. Maybe you can do something with this. When I factor this sum of 2 cubes out, this is n cubed plus 4 cubed, so this factors to n plus 4 times n squared minus 4n plus 16. That's your sum of 2 cubes thing. So they both share n plus 4s. You don't want to divide them out because they count as solutions, but if I add this over, now this is kind of a factoring by grouping. If I add this over, it's n plus 4 times n squared minus 4n plus 16, and then this is plus 12 times n plus 4 equals 0. So, in terms of factoring by grouping, n plus 4 is a common factor in both of these. So when you factor n plus 4 out, you're left with here n squared minus 4n plus 16 plus 12 equals 0. Does that work? Oh, this wasn't 12. This is 12n. Excuse me. 12n. 12n. Okay, like that. And then negative 4n plus 12n is 8n. So that is n squared plus 8n plus 60. So this does work. So maybe they were looking for us to do that. I wouldn't have sought that to begin with. That wouldn't have been my go. But it does skirt past needing to use the rational root theorem immediately, I suppose. And this gets to our sum and difference of 2 cubes. So n equals negative 4, multiplicity of 3 is the way to go about it. So here's an alternative way to do this. Maybe the way that they were expecting. I don't know. It's there. Let's see if that works again on number 12. It should. This should work again on number 12 in the exact same way. The reason I bring this about is because y cubed minus 27 is also a difference of 2 cubes. So I'm falling into my own lack of having understood the fact that you can factor by grouping, probably not always, but in this particular case, you can factor by grouping by the leading term and constant term-ish when it's a perfect cube. So this is kind of weird. This is y cubed minus 3 cubed, which factors into y minus 3 times y squared plus 3y plus 9, 3 squared. And this equals, you factor out 9y from here, you get y minus 3. So let's subtract the 9y times y minus 3 over to this side so we can look at this in terms of factoring by grouping, do the same thing. Y minus 3 is a common factor of both of these, so when you factor y minus 3 out, this time we'll write it on this side, I get over here y squared plus 3y plus 9 minus 9y. That's what remains after the factorization there. And 3y minus 9y is negative 6y, so you are back to where we were before. Okay, so this now factors down to y minus 3 times y minus 3 quantity squared, or y minus 3 quantity cubed. Therefore, y equals 3, and this has a multiplicity of 3, like that. So there are other ways to go about it, I suppose. I don't mind doing rational root theorem since we're in the proper section for it. That's nothing I would have known before. The way they set up the problem led me to try it out. It seemed to work. Awesome discovery with you guys. This is why I do some sight reading. I hope you learned something from it. I hope you determine your own ways to do it in the future. Okay, let's move on to exercises 13 to 20, where we find the zeros of the function, then sketch a graph of the function. This is where we get to do our tableless graphing and list out some of the features as we go to work. We have to understand end behavior based on the leading coefficients and degree. We have to find x-intercepts, y-intercept, and I still don't know what kind of graph axes I'm going to use. We're going to figure that out shortly. Okay, number 13. Number 13, we have h of x equals x to the fourth plus x cubed minus 6x squared. Now, the very first thing I want to call attention to, again, they didn't really seem to hit it hard in this section. They talked about it, but not heavily, probably because it was already in a previous section. The leading coefficient is a positive 1. All I care about is it's positive. The degree of the term is a quartic. That means it's even. All I care about is that it's even. Okay, even. So an even positive will have a start up, finish up kind of appearance like this. They won't always look like that, but that's the end behavior. That means I'm going to start from the top and finish at the top, right? Now, what I do have in this thing here is a common factor of x squared. When you factor x squared out, you're left with x squared plus x minus 6. If you continue your factorization, this factors into x plus 3 times x minus 2. If you're trying to find your x-intercepts, your zeros of this, you set this equal to 0, but bottom line, your x-intercepts are, in this case, 0. Now, 0 is important to state that this has a multiplicity of 2. This is where it's going to be very important that you understand what this means with regard to the graph. And negative 3 and 2. So I'll go ahead and use the standard, let me get it. I'm going to go ahead and use one of these standard graphing metrics here. By the way, the y-intercept is also 0. That's something that we could have pulled out from the original part. There is no constant. That means your constant is 0. And because an x-intercept is 0, I think it makes sense that your y-intercept is 0 here. So we have negative 3, 0, and 2 as your x-intercepts. Now, I ask you, as a quartic function, which needs to start up, finish up, how is it possible to only cross through 3 of these right here and do exactly that? It looks like it will just finish down. You could say, oh, just make it go back up. No, you just crossed an x-intercept that wouldn't have been there. What we have to do is really tailor to this multiplicity. This 0 with a multiplicity of 2 means that with this 0, it's either going to bounce off this way or it's going to bounce off this way. It's going to bounce off like a quadratic. That's what will get you the proper end behavior you were looking for. So although I'm not hitting any known exact points as I'm going through these, let me use blue. Although I don't know for sure what points I'm hitting going through here, I do know that I'm crossing these x-intercepts. I'm crossing through that one. I have to curve back up at some point, hit this 0, and bounce off of it. I'll bounce off of this 0 right here. I'll touch it, go back down, and then I'm going to come up through 2 like that and cross through, and there's a sketch of my graph. The reason why I don't love the fact that I'm using the x-y axes is besides the scaling right here, I can't guarantee that any of these are what they are. I wouldn't anyway, but I'm not using a table is the point. So did this hit at the bottom right there? I don't know. But I do know that it has to start up, finish up. I know that it has to hit those points, and the factoring concludes that. All right, that's number 13. Let's go to number 14. F of x equals x to the fourth minus 18x squared plus 81. Now, this is also a quartic function with a positive leading coefficient. So, once again, LC is positive. degree is even. We are going to start up, finish up. That's the important stuff I need to know out of that. Let's write these on the side. I want more room to just factor. This is quadratic form of this factorization. This is actually x squared minus 9 quantity squared, because if you consider this as, if you had trouble with, well, how'd you do that so fast? This is u squared minus 18u plus 81. This two numbers that multiply by 81 and add to negative 18 are negative 9 and negative 9. So this is u minus 9 quantity squared, which brings you to x squared minus 9 quantity squared. Now, x squared minus 9 is a difference of two squares, so that can factor into x minus 3 times x plus 3. Now, both of these would, in separate ways, be x minus, because it's x squared minus 9 squared, there are two of these as well, right? The book probably broke it down better by showing two different x squared minus 9s and merging them together, but this still works in that way. So, with that said, your x-intercepts of these are 3 and negative 3. Now, each of these are with a by a multiplicity of 2. For each of them, boom and boom. Which means on these intercepts, we will be bouncing off. They throw you right in the deep end of these graphs and say, you're going to deal with multiplicities of 2. I do wonder if they'll give us multiplicities of 3, given that they didn't actually teach it to you, even though I'll be happy to teach it to you if they show up. So with respect to this graph, we cross at 3 and negative 3 only. Now, I didn't mention the y-intercept. The y-intercept of this is 81. So let's write that. The y-intercept is 81. Now, I'm not really choosing to do any true scale of this thing. I'm going to call this one 81. Okay? Let me actually do it in black. I'm just going to call this one right here 81. Great. I'm not going to say, hey, these go by 27s, because I'm not choosing to do anything else on y other than that. So it does cross the y-axis there. Now, as I stated, it will start and finish up because an even degree, positive leading coefficient. So it does start from the top. It crosses through it touches negative 3, but bounces off of it. It's got to hit this y-intercept of 81. It's got to come back down and hit this 3 and bounce off of that one as well as it finishes up there. Probably not the best looking curves with the graph. It should be more symmetrical and such, but that is the nature of this graph. That's what your answer is basically going to be. Okay, number 15. Number 15, we get p of x equals x to the 6th minus 11x to the 5th plus 30x to the 4th. Let's talk about a couple other things first. We have the positive leading coefficient of 1. Did I write positive? Oh, I did the plus sign. It's positive. And degree is even, once again. So it'll start up, finish up. This one's different. It's a 6th degree, but, it still works the way that it does. Now, as far as factoring goes, x to the 4th can factor out of there. You're left with x squared minus 11x plus 30, which that part can factor into x minus 6 times x minus 5. That's as far as we can factor it. We do have 3 different solutions. We do have, or x-intercepts, I should say. Well, you can say solutions. You have x-intercepts of 0, 6, and 5. At 0, you have a multiplicity of 4. Now, they mentioned even degree multiplicities will still bounce off. This one would technically bounce off wider. It would go down to its sharper, it would bounce off wider, but that's neither here nor there for us. We'll just kind of sketch the graph as we know it. So we got to hit 6 and 5 as well with these other things as we start up, finish up. There's no limit to how many different start up, finish ups of these we're going to have. So, and by the way, the y-intercept is 0. There's an x-intercept of 0. There's no constant. The y-intercept here is 0. So 0 and 5 and 6. We got to start from the top. And we're going to finish at the top. Now, this is going to come down pretty sharp. I don't know how so, but it's going to bounce off of this thing and come back up. And it's got to come back down and hit 5. And it's got to come up through 6 afterward. I'm going to redo that. I'm going to do it from wider. Hit up there and get a little farther out as I come back here. Come back down through 5 linearly and come up through 6 linearly. It's actually going to cross through these ones. How do I know that? Because they have multiplicities of 1. That's the appearance that this graph's going to take on. Sorry, that should kind of curve up a little more sharply than that, I guess. And there's some look of the graph that I'm just going to go ahead and have. Okay. Okay, let's see if we can get some different kinds of changes and characteristics of these graphs. Number 16. Aha, this will have some differences. Number 16. We have g of x equals negative 2x to the fifth plus 2x to the fourth plus 40x cubed. Okay, this time the leading coefficient is negative. Should I put a minus sign? I don't know what I should do. Let's do a minus, but let's put parentheses around it. Negative, and the degree this time is odd. Now, a negative leading coefficient with odd degree is going to start up but finish down. It's going to have something like this going on. I don't know how exactly, but it's going to have something like that going on. Start from the top, finish at the bottom. Notice how you're going to be crossing through those. Now, let's begin factoring this. The y-intercept appears to be 0 again. I can factor a negative 2 out of here, and x cubed. Oh, I got to talk about this one. The book didn't really talk about this one, but that's okay. I'll show you the graph. You can try this on a graphing calculator and see. But this will end up giving you x squared minus x minus 20. That factors to x minus 5 times x plus 4. So your x-intercepts in this case, your x-intercepts are, once again, 0 and 5 and negative 4. Now at 0, you got a multiplicity of 3, which is really interesting. This is a different kind of one than you've seen before. I teased it, but now we got to actually do it. Now the book did mention that anyone with an odd degree will cross through that x-axis as opposed to bouncing off of it. But it does technically cross differently. I could show you. I will go to the graphing calculator and show you this one in a bit. But 0 and 5 and negative 4, we do have to start up, finish down. It will go through 0 linearly, but it's not just going to be. It's going to take on this appearance, sort of, but it's not just going to be that. When it goes through 0, guys, it's going to go through 0 a little more like this. I'll draw it better, but it's going to have a cubic appearance to it. You might not have graphed cubic functions before, but it's going to kind of squiggle through. It has to do with the nature of how you plug the numbers. You know, if you did use a table, truly how it would go through. But that's what it's going to do. We're going to start from the top. We're going to go through negative 4 linearly, if you will. And when we go through 0, we're going to kind of snake on through. It's kind of a squiggle. It's going to go through like that and back up like that. It's not going to bounce off. It would do what bouncing off does, but the sign changes to positive. And then it's going to go down linearly through 5, like so. I could do this better, however. Okay, not the best appearance, kind of close enough. So that's going to be the appearance of this graph. A little different, right? A little different, but that is its appearance. Now, I'd love to do this graph for you on the graphing calculator to kind of demonstrate what it is I'm talking about here. So let's get that one typed in. Let's punch it in here. Let me get a window range that'll work here. We only need to go from negative 6 to 6 on x, and let's see what kind of heights will be required. I'm not sure. I'm going to stretch it out a little bit. So let's plug in negative 2x to the fifth plus 2x to the fourth. I want to plug in the original, right? Make sure that I got what I was supposed to out of it, you know? Plus 40x cubed. Okay, so let's look at this graph given this window range. It's a different one, but just look at the behavior of it. It's going to go down. Whoa, that's pretty sharp. But you'll see the curve through there. Okay, I need more. I need significantly larger y values. Let's see if negative 100 and 100 will do. Geez, those went really tall. See, we don't know our relative mins and maxes of it. That's kind of the problem with this. That still goes sharp. Guys, this is a sharp graph, but you can see that cubic bounce through here. I'm going to keep going, man. This graph is tall. This is tall. Negative 250, positive 250. How we doing? How we doing? Still not enough. And you still see that cubic and the cubic middle behavior right there. Not even nearly enough. Wow. Negative 500 and 500. Come on. Let's hit it. Let's find them. Okay. I still didn't hit a top one, but you're really starting to see it. All right. Negative 500 is good on the bottom. Let's go to 800. Yeah, let's go to 8,000. Yeah, that'll do. Let's go to 800. So this just goes to show that, wow, those relative mins and maxes are quite. Why don't I just get it right the first time? I'm sorry that you have to explore this with me. Just go to the next problem. Go to the next problem. Hey, we found a top. Okay, But you do see the nature of this graph. It starts up, finishes down, it hits -5, and it hits 6 as your, -4. It's -4 and 5 as your x-intercepts. It hits 0, but it doesn't go straight through 0. It curves through 0 like a cubic function. There's the nature. The other thing I just might as well mention, as I did a lot of poor, terrible trial and error on this thing, is that these relative mins and maxes, that minimum and maximum, this is in the thousands. This is in the hundreds, negative hundreds right here. My graph, like I said, I just chose these things right here. I don't know how low this thing goes. Clearly, it doesn't just go down to about -5 and up to about 4. These things go super tall and super small, and we can't account for that stuff, right? We're not using a table technically right here, and we're not using calculus to get those relative mins and maxes. So that's why I said standard graph paper might not be technically accurate to what we should do here, but I'm going to use it anyway. So there's the graph of that guy. That looks good. I'm going to move on forward. But that's an example of the cubic function. I really did have to point it out because the book didn't. And that's the first time we saw one of that nature. Okay, number 17. Number 17, we have g of x equals -4x to the 4th plus 8x cubed plus 60x squared. Our leading coefficient is negative. Our degree is even. Therefore, this will start down and finish down. Start down, finish down. Okay? Now, as far as common factor goes, because they all seem to have one, we got -4x squared can factor out of here. And then you're left with x squared minus 2x minus 15. As I continue the factorization of that quadratic trinomial, that factors into x minus 5 times x plus 3. If -4x squared equals 0, then x equals 0. That's one of your x-intercepts, but it does have a multiplicity of 2. I'm just going to put times 2 at this point. Multiplicity of 2. This has an x-intercept of 5 and an x-intercept of -3. Our y-intercept is 0, as the x-intercept is 0. So we'll go ahead and construct that graph. Remember your multiplicity of 2. Remember your end behavior. Work that out. Yeah, I didn't expect the graphing to come in this section. When they said solve the equations, I assumed it meant in non-graphing ways. But we are solving here technically, and now we're showing the use of solving them. Why we do and what they mean, what multiplicity means and all. So here are our x-intercepts, -3, 0, and 5. It will bounce off of 0. So we do go through. We start from the bottom as we go through -3. When we hit 0, we bounce off of it. Then we got to go back up and find our way down through 5, and we do go through 5, and we finish at the bottom right there. These are linear multiplicities of 1, yada, yada. There's our graph. Are these the true relative maxes? Highly doubtful. I'm sure they're a lot taller than that. We can't quite account for it, so we'll move forward. Number 18. H of x equals -8x cubed. Sorry if you hear humming in the background. Let me take care of something. Hold on. Okay, I only just now realized there was a fan blowing in the background in another room. I thought it was my AC, but it was just a fan. So I don't know if the humming's changed or not, but anyway. Okay, number 18. H of x. It's a lot quieter for me now. I was like, I got it. No. H of x equals -x cubed minus 2x squared plus 15x. Okay. Y-intercept of 0 again, as there's a common factor of x. 0 is going to be an x-intercept, you know, as we've seen. Leading coefficient is negative. The degree is odd. It's a cubic. So we are going to start up, finish down, right? That's the nature. So we factor a -x out of here, right? Always factor out negatives, as you've seen before. And we get x squared plus 2x minus 15. Now, we just saw a close factorization to this with the minus 2x minus 15. What's going to change now is this time, the 5 in the factorization will be positive, and the 3 will be negative. X minus 3, like that. So there's the factorization of this. Now, our x-intercepts this time are 0, -5, and 3. None of them have multiplicities other than 1. None of them are repeated solutions. So when we graph this, they're just going to go through. They're just going to go through all these points. This is a more standard kind of problem with this. Let me just plot it right there. I want to fit these, you know? I want to fit it. All right, so let's give it a shot. -5, 0, and 3. It's negative odd is going to start from the top and finish down. So we have to go through this one, come back up and hit 0. We're going to come through this guy right here. It's harder for me to do this on my stylus. It's probably easier for you on paper. And I'm going to come back through this one and down like that. No different kinds of multiplicities. It just behaves like a linear. It's just going to do what it does and continuous path. That's a little better. Okay, I'm going to use that. So there is the nature of that graph. Always draw your arrows because it's going to continue downward. That is the end behavior. It never kind of comes back up and does anything like that. The only times it hits the x-axis are there. All right, 2 more numbers, 19 and 20. Number 19. H of x equals negative x cubed minus x squared plus 9x plus 9. Some things I recognize are different from this problem from some of the other problems. First of all, no common factor. Second of all, I see that we also have a y-intercept of 9. I'll just put 9, positive 9. So we're going to cross through the y-axis there. We still have to do some factoring. Negative leading coefficient. Degree is odd. Another startup finish down. But in kind of a different way. I'm going to factor negative x squared out of the first 2 terms. Sorry, this is factorable by grouping. Factorable by grouping. So in factoring by grouping, factor negative x squared out of here, you get x plus 1. Factor a 9 out of here, whoops, you get x plus 1. And now this thing here becomes, here's the thing. I'll talk about it when we get there. X plus 1 is one of your factors. Negative x squared plus 9 is the other. Now, this has a leading negative in that factorization. I'd like to factor that out as well. I was going to say I can factor it out in total. I don't want you to see it like that. It would look kind of wonky. So let's factor the negative out now. You get x squared minus 9. And here's still that x plus 1. That doesn't change. And x squared minus 9 is the difference of 2 squares, which factors into x minus 3 times x plus 3. So you get these 3 factors alongside the negative. That's just part of the leading coefficient biz. Doesn't affect your x-intercepts. Your x-intercepts are 3, negative 3, and 1. All multiplicities of 1, so they're just going to cross through there. It is negative, odd degree. It's going to start up, finish down. Let's go ahead and make that work. This is kind of all I need. Oh, and a y-intercept of 9. And a y-intercept of 9. Now, should I just plot it at 9 up here or change my scale? I'll just plot it right there. It might look a little strangely tall, but we'll go there. 3, negative 3, and 1. 3, negative 3, and 1 are your 3 there. Okay, so we're going to start up, finish down. The way this has to work is it has to start from the top. How's that going to work? It's going to start from, wait, hold on. Was it 3, negative 3, and 1? Oh, this is a plus 1. I'm sorry. I was going to say this won't work. Okay, that's a plus 1. This is a negative 1. So therefore, this has to move over. See, this is why things. This is why things need to work. So anyway, this needs to be a negative 1. Now it'll work. Okay, let's try that again. So we are going to start from the top. We're going to come through negative 3. Come back up through 1. And then we got to hit that 9, right? The y-intercept. So we got to come up and hit that 9. Now, is the 9 necessarily the top? No. Should I pretend like it's the top? Not necessarily. Let's actually do this. Let's go up through the 9. And let's curve back down maybe at the top right there. Whatever, right? We don't have true scaling of anything else, but it does have to hit 9. And it's got to go through the 3 there. So if there's a better version of that graph, there you go. Maybe next time if we have something so tall, I would just change the scaling of the entire graph. But that is how the graph's going to work. See, this wouldn't have worked if the x-intercept was over here, because I was saying, how am I going to hit 9 without crossing back through there and hitting that? And then how am I going to cross through here and do it? It wouldn't have made any sense. So that's where I was questioning my x-intercept, and rightfully so. All right, number 20. P of x equals x cubed, so it's a positive x cubed, minus 5x squared minus 4x plus 20. All right, we got a y-intercept of 20. We have a positive leading coefficient. We have an odd degree. It's going to start down, finish up. This time we're going to go this way. We got to cross that 20 at y. Keep that in mind. X-intercepts are revealed by doing factoring. This is factorable by grouping. We can factor x squared out of the first two terms, get x minus 5. Factor negative 4 out of the next two terms, get x minus 5. This will factor into x squared minus 4 times x minus 5. You know what I should have done for the previous problem? Let me just go back to it for a second. I always talk about always find greatest common factors first. This does have a GCF, right? This, technically, I should have factored the negative out to begin with. Then it probably wouldn't have confused you on what happens next. I should have started with that, and you can see how the negative now comes into an existence later. But anyway, just bringing that up. I just thought about that now. Okay, anyway, back to this problem. This difference of two squares is x minus 2 times x plus 2. Yeah, sometimes my mind, although I'm doing this problem, my mind is running through obviously a lot of things at once and haywire. And I can literally be thinking about another problem as I'm doing this one. There is the full factorization of this one. We have x-intercepts of all multiplicity of 1. They seem to really shy away from the multiplicities later, which is interesting. Normally it seems like they go the other way and make it harder later. So 2, negative 2, and 5, we got to cross through a y-intercept of 20. So as we do this graph, I definitely got to change the scale this time. We don't really have to go by a specific scale given no other point exists for us beyond just that 20. So let's just pretend the 5 instead is a 20, that these are going by 4s. So there's our 20. And then we do hit that as we also hit 2, negative 2, and 5. It is a positive cubic. So we are going to start. When I say start from the bottom, I mean the leftmost point we're going to cross through comes up. We're increasing as we go through it. Hopefully that's totally made sense if I said that. Let's pretend 20 is the top. We're going to go back down through 2. Hit some bottom. No. Hit some bottom here before we come up through 5. And again, nothing else is known to be true to scale. I don't know. We're bottoming out at, 3.5 comma negative 4. We're not using a table for that. I don't think that's necessarily a concern for our graphs right here. We're using the features, and that's the goal. Okay, there are our graphs. Let's move forward. Number 21. Using equations. According to the rational root theorem, which is not a possible solution of the equation 2x to the 4th minus 5x cubed plus 10x squared minus 9 equals 0. Okay, so for this equation here, this is probably where they're introducing rational root theorem, even though I gave you a little taste of it on numbers 11 and 12. Gave you a taste of it on numbers 11 and 12. We actually used it, even though I don't know if they wanted you to use it yet. All right, your possible p's over q's here, guys, your possible ones, you take your factors of your constant, 9, and those are 1, 3, and 9. And divide them by your factors of your leading coefficient 2, which are 1 and 2. That means all your possible rational roots are plus or minus 1 over 1, plus or minus 3 over 1, and plus or minus 9 over 1. And then plus or minus 1 over 2, plus or minus 3 over 2, plus or minus 9 over 2. These are the only possible rational roots in existence. This is how the rational root theorem works. So which is not a possible solution? Negative 9 is a possible solution, so that is not the answer. Negative 1/2 is a possible solution, so that's not the answer. 5/2 is not a possible solution. 5 is not a factor of 9. Therefore, this is the answer because it's not a possible rational root. 3, as you can tell, is also on that list. So 5/2 is not a possible rational root. Interesting way to ask the question, but it still works out. At least for a first question. Assuming that is the first time they expected you to use rational root theorem, it's fine. It's perfect. We're talking about listing rational roots. We got to know how to do it. All right, number 22. According to the rational root theorem, which is not a possible 0, which is not a possible 0 of the function. I'd say the same thing is involved in this kind of question. You're testing rational roots. I think they want you to know that the word 0 represents the same thing as roots when it comes to this. The difference is this time the equation is written as a function. The idea of that is you're supposed to set y equal to 0 when it comes to solving for x in this situation. Now, there's a lot of stuff that's being written. Honestly, none of this stuff matters to us when it comes to what we are testing for possibility of rational root. or whatever, 0. Not an actual rational root, but possibility. The only thing that matters to us is this number and this number. And it doesn't matter if they're positive or negative, truly, as a whole, when it comes to our tests of numbers. So, P over Q values. There are many different possibilities for negative 36 for rational roots. There's factors of 36. 1, 2, 3, 4, 6, 9, 12, and 36. Is that it? No, I'm missing one. 18. 18 and 36. Maybe it's better to list them out as like what they are. 36 times 1, 18 times 2, things like that. 40. There are a lot of things of 40 as well, or at least enough. 1, 2, 4, 5, 8, 10, 20, 40. Quite a few, right? So there are a lot of ones. If I were to list out all the rational roots, it would kind of take a while. Plus, I don't know if it's worth me writing them all out. I don't know how often we're going to have to do it. Maybe for the sake of this problem, I will do it just so we're not just answering the question itself. I want you to know what this looks like. We got to divide all these by 1, which is a way of just saying plus or minus 1, 2, 3. Listen, there are going to be a lot of them. I want to show you why sometimes it's more beneficial to just use the calculator when to list these out. So here are some of them, many of them. Then we got to divide these numbers by 2. Now keep in mind, dividing an even number by 2 will probably get you a number that's already on this list. 1 over 2 is not on the list, but 2 over 2 is on the list because that's 1. We got 3 over 2. 4 over 2 is 2, so that's already on the list. 6 over 2 is 3, that's on the list. 9 over 2 is not on here. So, don't list duplicates. 12 over 2 is 6, we have it. 18 over 2 is 9, we have it. 36 over 2 is 18, we have it. So we move forward. Again, if something divided by 4 is already on the list when reduced, we don't include it. So 1/4 is not on the list. 2/4 is 1/2. That's already on the list. 3/4 isn't on here. I think if the thing reduces, then it's already on the list. The halves and things like that. So just go with ones that can't reduce. How about that? 4/4 reduces, 6/4 reduces, 9/4 does not reduce. So plus or minus 9/4. 12/4 reduces, 18/4 reduces, 36/4 reduces. So again, I'm imagining that all those numbers are already on there, like 18/4 is 9/2, things like that. Divided by 5, none of these will be on the list. So guys, I'm answering the question, but I'm also giving you all the possible rational roots. I don't think this is really what they necessarily expected, but this is a goal of me teaching to you how exhaustive. This is one of the more exhaustive lists you'll ever see. I don't really ever see these as often. They don't choose numbers like this quite as often. But you got to divide these all by 5 now. And when we say these are the possible rational roots, I mean, there are only up to 5 of these in this entire list. And so this is quite the list. None of these can reduce, so all these are unique numbers right here. But then they wouldn't be later. Dividing them by 8 now. So again, just make sure it doesn't reduce. So 1/8 doesn't reduce, or 3/8, basically odd numbers. 9/8, plus or minus 9/8. And I think that's it for that. Yeah, 1, 3, and 9. It's those numbers, 1, 3, 9, 1, 3, 9, whenever we're dividing by evens. 10, so same thing. 1/10, 3/10, 9/10. Again, anything else reduces to something we've already seen. At least that's a little helpful. 20, what do you say? 1/20, 3/20, 9/20. And keep in mind, when we say the plus or minus, that means we're technically doubling up this list. And 36, 1 over 36. Oh, 3 over 36 reduces. I got to be careful. 3 over 36 is 1/12, which is not on this list. I hope I didn't skip by anything else that doesn't reduce, but anyway. 9 over 36 is 1/4. We already have that on the list. Okay. Oh, I'm sorry. This isn't over 36. That's why. It's over 40. I was like, why did this break? These are over 40. I very much apologize. I was saying, what's going on here? All right, 1/40, 3/40, 9/40. Okay. Way overdoing this problem beyond what's expected. We should just be able to look at these things and say what are factors and be good to go. Okay, so I apologize that I'm doing more than the problem's asking, but I'm teaching you something about rational root theorem. Bottom line, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. 36 different factors, times 2. 72 different possible rational roots of P over Q. Now, which one is not a possible rational root for this problem now that we've gotten there? Negative 2/3. 3 is not a factor of 40, so it's not possible, right? That's as easy as this question would get with respect to these. Negative 3/8 is on my list right there. So that's not it. 3/4 is on my list right there. So that's not it. And 4/5 is on my list right there. So that's not it. But negative 2/3 is not on my list because 3 is not a factor of 40. So yes, I went above and beyond when it came to the problem, but hopefully we're addressing how rational root theorem things work. And hopefully I'm not going to have to do as much of that ever again. All right, number 23, error analysis. In exercises 23 and 24, describe and correct the error in listing the possible rational zeros of the function. So we're going to have to correct it afterward. So in number 23, they have the possible rational zeros of f. Let's take a look at their list. They're choosing factors of 45. That would be 1, 3, 5, 9, 15, and 45. Do they have those numbers? Yes. Now, they divide them by factors of 1, which is just 1. So 1 divided by 1 is 1, 3 divided by 1 is 3, 5 divided by 1, etc. But what are they missing? They're missing the negative possible ones. The negative possible rational zeros are not included. So if I write out this list, it's not going to be an exhaustive one. They have all the numbers right, but now it's plus or minus 1, 3, 5, 9, 15, and 45. So there's the correction to that problem for our P's over Q's, possible rational zeros of f. There's number 23. All right, number 24, possible rational zeros of f here. They have 8. Okay, so the problem is they swapped the things. As far as our P's over Q's go, these are our P's, these are our Q's. So they have these swapped. They did factors of Q on top, factors of P on bottom. They got to do factors of P on top, your constant, factors of Q on bottom, your leading coefficient. Your factors of your constant, the factors of the constant term are on bottom, are in the denominator, when they should be up top. And the factors of the leading coefficient are in the numerator, when they should be on bottom. So flip them. Flip them. What are our factors? Now, generally, when I do my own P's over Q's, I tend to kind of list the factors as like a whole set. But factors of 8 are 1, 2, 4, and 8. Factors of 3 are 1 and 3. So I start with that, and then I just start kind of dividing them out. So I'll say, okay, so that's going to be plus or minus 1 over 1, 2 over 1, 4 over 1, and 8 over 1. And then divided by 3, plus or minus 1/3, 2/3, 4/3, and 8/3. Ugh. Got it. Okay, so that would be the set there. Again, they had to swap them, and we have it. Oh, that was number 24. Sorry, I did not move this one down. Okay, number 25 to 32. I have to go down to the next page after. So we start seeing 25 and 26, but find all the real solutions of the equation. Real solutions. That means they don't always have to just be rational. There may be irrational ones, maybe imaginary. I don't know if they're going to go that road. They haven't done that yet for us. But see some complex conjugates. So plus 15 equals 0. Now, I'm going to solve this using any means necessary, meaning if I can factor by grouping or something like that, I will. Can I factor this by grouping? No. So they're probably going to set up problems where you can't. So what we got to do is use rational root theorem. Let's list our P's over Q's, and we're going to do factors of 15, 1, 3, 5, and 15, divided by factors of 1, which is 1. That means our possible rational roots are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. There are 8 different ones to test. Now, y'all, I just want to let you know, and I've said this in the lecture, and I've already done it a couple times, my goal for these problems is to find one of the rational roots and then use synthetic division to divide out. Generally, I like to do these in a faster way. I already actually see one of them. because it's one of the easier ones. Plugging in 1 is always really easy for this because you just let the coefficients be what they are. Remember, these are 1s, right? 1 cubed is 1, 1 squared is 1, and this would be 1 plus 1 minus 17 plus 15, meaning 1 actually works. 1 actually works here. Now, I know these aren't f of x equations, but I'm going to treat it like it to just let you know that, hey guys, f of 1 equals 0. Generally, what I would do, like I stated, is I would use the graphing calculator until I find one that works, but because 1 was so easy to find, I'm pretty good to go from there. Now, I like to plug them in to work it out if I can do it mentally, or I like to do it on the graphing calculator, and then I use synthetic division on it. So if f of 1 equals 0, 1 is one of my roots, I will now use that 1 root and use synthetic division on this with 1, 1, negative 17, and 15 as the coefficients. Let's do this. And with the 0 remainder as expected, we now have factored this thing into, remember, if 1 is the root, then x minus 1 is its factor. And this factors into x squared plus 2x minus 15. We've seen that before. This equals 0. We continue solving by factoring. If factorable, it is x plus 5 times x minus 3. And this becomes x equals 1, x equals negative 5, x equals 3. There are your solutions. Now, there's more that I want to state about the whole when I use the graphing calculator, because I am at some point going to do it, but I'm going to do some to kind of show you what the book would do if something is too far out, as in plugging in 1 doesn't work. But some of them, plugging in 1 will work, and if that's it, I'm just going to use it, right? And then I'll solve the rest of the way if I'm able to. So x cubed minus 2x squared minus 5x plus 6 equals 0. Your possible rational solutions here as p's over q's that we want to test are plus or minus, let's try this, because they just divide by 1, right? Factors of 6 are 1, 2, 3, and 6. So plus or minus 1, 2, 3, and 6. So let's start by testing 1. This would be going to be easy. 1 minus 2 is negative 1. Minus 5 is negative 6. Plus 6 is 0. So that does work. F of 1 equals 0. That means 1 is a rational root. We'll do the exact same thing as last time. Use synthetic division on this with 1, negative 2, negative 5, and 6 as your coefficients. Let's go. Whoops, negative 6 and 0. So with that 0 remainder, as expected, we now can factor this once again into an x minus 1 times, and this is x squared minus x minus 6, and this is set equal to 0. That guy's factorable. It factors into x minus 3 times x plus 2. So just like the last problem, a cubic, 3 solutions, x equals 1, x equals 3, x equals negative 2. Okay, let's move on and see how the rest of these work. I'm expecting great things, great things. Number 27. X cubed minus 10x squared plus 19x plus 30 equals 0. Cannot factor by grouping. Our p's over q's, once again, our leading coefficient is 1. And I think, listen, when we see our numbers here, leading coefficients on all these are 1. This is just 2. This is just 3. Like I said, they're not going to do that thing where it's 40. You know what? You notice how, you know why we had so many things listed? Because we had to use all the factors of 40 and do that. They're going to be a lot nicer to you on those problems. I listed those factors because I was the mean one. I was the one that, well, I was mean to myself, but I was the one that had to make you slog through all the possible factors when it can get really big like that. And generally, that's not going to be the case. Anyway, here are factors of 30. Here are factors of 1. I should have actually left that alone and just went straight to this. Plus or minus 1, 2, 5, 6, 10, and 30. I kind of hope that 1 or negative 1 isn't one of them this time. I'd rather proceed forward here. All right, let's try 1. You get 1 minus 10 plus 19. No, that's not going to work. Negative 1 minus 10 is negative 11. Minus 19 is negative 30. Plus 30 is 0. Negative 1 does work. So f of negative 1 equals 0. Now, here's the thing. The book asks you to use synthetic division until you get a 0 remainder. You don't have to do that. You can substitute values into there. Remember, they taught you the remainder theorem was very much so that it's the same as evaluating a function for it. So whichever one you choose. So as I was trying 1, remember, this one did work. I'll write this. F of 1 equals, let's see, I didn't see what it equaled though. 49 plus 50, 40, I think. I think f of 1 equals 40, so that means that one does not work, and f of negative 1 equals 0 means it does work. That also means if I did synthetic division with 1 on this, I should be getting a remainder of 40. So if we did the test they would have done this. 1, negative 10, 19, 30. 1, negative 10, 19, and 30. They would have done this. They would have gotten 40. They would have shown that, okay, that doesn't work. And then they would have done it on negative 1. So whichever one's kind of fastest to you is kind of your call, right? For me, graphing calculator is the fastest thing. And you will bet that I'm going to do it as long as, I mean, it looks like we're getting some pretty easy ones to work with so far. Maybe that's why they're saying don't use the graphing calculator. You know what? I'll do what I do. Anyway, so here we go. Okay, our goal of synthetic division is to get what this polynomial is after getting negative 1 as your root. If negative 1 is your root, then x plus 1 is its factor. This is x squared minus 11x plus 30, which too is factorable. That factors to x minus 6 times x minus 5. Therefore, using zero product property, x equals negative 1, 6, and 5. I'm going to write it like these probably now. Save whatever time in ink that I can. This all runs on ink, right? Smart ink. Number 28. X cubed plus 4x squared minus 11x minus 30 equals 0. Again, the factors of q are just, 1, negative 1. So I'm going to write these straight up. Factors of 30, 1, 2, 3, 5, 6, 10, and 15, and 30. Whoa. Did I miss? Hold on. I missed some factors here, guys. 3, 15. I was probably talking during that time. Sorry about that. Hey, you know what? We found one beforehand. We're all good. And look, they weren't answers here. Pff, come on. I was wondering, I'm like, wait, didn't we just do this list, but doesn't this look bigger? So my apologies, y'all. We got him. Okay. Anyway, same factors as before, but not necessarily the same roots. So we try some. Plug in 1. 1 plus 4 minus 11 minus 30. That's not 0. Plug in negative 1. Negative 1 plus 4 is 3. Plus 11 is 14. Minus 30 is negative 17. That's not 0. It gets into that stage where I'm just going to try 2. If that doesn't work, I'm going to go to the calculator. The answer may be negative 2. I don't know. But try 2. 2 cubed is 8 plus 2 squared 4, 16. So this is why I'm going to use the calculator. 8 plus 16 is 24. Minus 22 is 2. Minus 30 is not it as well, right? So I'm going to go to the calculator, guys. I'm just going to go ahead and use the thing from there. The next one might be negative 2. But see, I don't want to spend time not only plugging in those numbers, get super big ones and until it works. I also don't want to use synthetic division and write all that down. Now, you might have to, right? That's why I showed on this previous problem. You might have to do this. You might be forced to. You might not have a graphing calculator, whatever. You might be testing things until you get a remainder of 0, in which case it might take a while. I don't know how long it might take, but it might take a while. The good news is at least one of these will be a solution. Maybe a rational root. Maybe the other ones are. We don't know for sure. I don't know for sure, at least. Anyway, so I'm going to substitute this one in, even if it takes some time to substitute in. 4x squared minus 11x minus 30. So we'll show you that once again, that in asking mode, that those ones wouldn't have worked. So 1, negative 1, and 2 do not give you 0. How about negative 2? Negative 2 does. So I spent all the time trying to get to there, find out that it finally works. So like I said, what you might have to do in these situations, and I'll do this one last time on your behalf because you might have to do this, either plug them in or use synthetic division on them and try and see them until they do work. So this one wouldn't work here. At least it's fast. It's just I don't like setting it up each time. So negative 36, that's not 0. And remember, negative 36 is the value that we had when plugging in 1, right? That's the idea of the remainder theorem. Now you try negative 1. You try negative 1. And let's see if we get negative 16, like we got negative 16 on the by plugging it in. We should. So this. So we get negative 16 that time. Again, no good. And then we try 2. Which also, we should get negative 28. Remember, I already plugged these ones in. They didn't work, but I'm showing you what you might have to do as a result of this. And how I'm going to use the calculator on this later, and how you can do your tests leading up to it, and how it might take some time. Just depends. Just depends on the problem they give you. So negative 28, and again, that's the value that they got. But negative 2 is the one, right? This one that'll work. This is the one we kind of have to do synthetic division on. This is the goal of synthetic division, getting that reduced polynomial after. Or the new polynomial after factoring. So 1, 2, negative 15. Aha. All right, so that one worked. So f of negative 2, assuming this was actually function notation, but f of negative 2 equals 0. Therefore, we have this polynomial. So this x cubed plus 4x squared minus 11x minus 30 factors into x plus 2 times x squared plus 2x minus 15. There are a lot of times we've actually had this factorization. Equals 0. That factors into x plus 5 times x minus 3, which becomes x equals negative 2, negative 5, and 3. So far, all of our zeros have not only been, I mean, listen, you won't get any fraction ones potentially until you hit something like numbers 31 and 32 because these coefficients here. But they've just been nice, good old integers. A lot of 5s and 3s from this set. All right, number 29. So from here on out, guys, I'm only going to use the graphing calculator until I find a rational root. Then I'll use synthetic division on that rational root. Understand what you may have to do as a whole until you get there. And I apologize if that's what you have to do. Like, I'm sorry. I'm sorry for you if that's what you have to do. That's what I mean. But still do those tests. You can still follow along with what I'm doing as needed, though. All right, x cubed minus 6x squared minus 7x plus 60 equals 0. I cannot factor by grouping. Your p's over q's possibilities here are plus or minus 1, 2. Let's not miss any this time. 3, 4, 5. There are a lot of factors of 60. 6, 7, 8, 9, 10, 11, 12, 15. And who knows? It might take a while. It likely won't. 20, 30, and 60. Did I miss anything? Let's see. I'm going to pair these up. 1 times 60, 30 times 2, let's see, 20 times 3, 15 times 4, 12 times 5, 10 times 6. Yep, got them all. All right, so those are the possible ones. If 1 doesn't work, I'm going to go to the graphing calculator. 1 did not work, so let's... I could have kept those on there, but let's see what we got. We got x cubed minus 6x squared plus minus 7x plus 60. All right, let's try some. 1 shouldn't work as far as what I saw. Negative 1, 2, negative 2. See how long synthetic division might take until you get your value? It took negative 3. Negative 3 is the first one. Now, remember what I said before. If you keep testing down the line for all your things, you will end up finding all of them. That doesn't mean those are the only answers, though. It depends on what kind of function it is. For a cubic, I expect 3 solutions. That doesn't mean something can't have a multiplicity, so we'd have to find that as well. So really just test until you find 1. Even if you use calculator, don't cheat your way through all the other ones. Just from here, I found out, that the calculator found out that negative 3 gives you a 0. So we'll use synthetic division on negative 3. And let's go to work on that one. Okay, so as that one works there, our factorization is x plus 3 times x squared minus 9x plus 20. I think we've seen that before as well. Therefore, this factors into x minus 5 times x minus 4. And your solutions are negative 3, 5, and 4. Okay. All right, number 30. Number 30. x cubed minus 16x squared plus 55x plus 72 equals 0. Cannot factor by grouping. We got some factors of 72 to take care of. We got 1, 2, 3, 4, not 5, 6, not 7, 8, 9. All right, so remember 8 is the split, right? 8 times 9, 12 times 6. 18 times 4, 24 times 3, 36 times 2. See, that's how I should be doing it. And 72 times 1. So those are all the possibilities. Just watch it be 72. Actually, you know what I think it is? I think -1 actually works. Now that I see, I think -1 works. I'm gonna trust that it works. Here, let's do this. I'll do it the way that we had it before. Let's try 1. Find that it doesn't work. Honestly, I'll just, plug it in. 1 minus 16 plus 55 plus 72. No, but -1. Let's go to -1 now that I established that. -1 minus 16 minus 55 plus 72. I think that's 0. So let's go ahead and use it. -1, -17, 17, 72, and -72, we get 0. All right, so that did pan out. -1 is one of the roots, therefore x plus 1 is a factor, and x squared minus 17x plus 72 is your other factor. When set equal to 0, we can factor that into x minus 9 and x minus 8. I don't know why I wrote that in opposite order. Therefore, x equals -1, 8, and 9. And keep in mind, that does mean that we could have used synthetic division on these ones, but those would have gone much farther down the list, right? I would have had to, if I skipped -1, I would have gotten, done these two and these two and these two and these two and finally hit 8, and then it would have worked. And if you're doing synthetic division on those until it worked out, it might take some time, right? It might take some time. All right, number 31. This is the first one where your coefficient, at least for solving, where your coefficient is not 1, your leading coefficient. That means we got to consider fractions, and that means at least one fraction answer will be had here. Probably only one. Okay, now our p's over q's, given that, first of all, there are no common factors, and you can't factor by grouping, our factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. Our factors of 2 are 1 and 2, which leads us to the following possible rational roots. The ones that divide by 1, like so straightforward. And then we divide them by 2. Now, I showed this in my big list on a previous problem where if a number divides by 2 that you already have, you leave it. Basically, if a number simplifies, then you probably don't do it. Otherwise, do the ones that become fractions. Plus or minus 1/2. Plus or minus 3 halves. Notice I skipped 2 halves because 2 halves is 1. Skip 4 halves because that's 2. Skip 6 halves, skip 8 halves, 12 halves, and 24 halves. Okay, so those are the only other ones that are possible because we have 24 halves as 12. We have 12 halves as 6, things like that. So these are the only other possible ones that should fit within there. Let's fit it. I can't. There they are. So 1/2 and 3 halves are possible ones there, but let's start with 1 and -1. I don't think those will work. I'm going to go straight to the calculator then with that in mind. So on the calculator, type in that equation, and let's find. Let's find 2x cubed minus 3x squared minus 50x minus 24. All right, let's plug in some numbers. Well, we already plugged in some. 1, -1, 2, -2, 3, -3. None of those worked. So we keep going. 4 and -4. All right, -4 is one of them. So you would have done 8 different tests until you found one, unless you started with the fractions, which then you would do up to 4 of them. Fractions are kind of tougher to work off of. So f of -4 equals 0. Awesome. -4 is our root, our rational root to work off of. And we get this polynomial, 2x squared minus 11x minus 6. So this factors into x plus 4 times that. Now, no one's stopping you from using rational root theorem again, or quadratic formula. If you don't know how to solve this quadratic by factoring, I'm only assuming it's factorable. I don't know that it is. But if you wanted to do that, you can test all other numbers. I want to remind you, as I just stated, that they may not be factorable. I have no idea. I'm going to go and try it right now. I hope it is. I assume it is. I hope it is. But, oh, you know what? It is. It's factorable. If it wasn't factorable, quadratic formula. If it is factorable, you can still test rational roots. And keep in mind, -4 may be another rational root that fits in here. But you can test all the other ones here until it works. But if you know how to factor, you can also go by factoring, of course. This factors into -6 and, I just had it, and 1. -12 plus 1 is -11, so that works out that way. If that's the case, x equals -4 is an answer. X equals 6 is an answer. And if 2x plus 1 equals 0, let me write this on the side because I'll say this out loud next time. I'd say subtract 1, divide by 2. And x equals -1/2. Right? That was the other one. So, -4, -1/2, and 6. Are they all on that list? -4 is on the list. 6 is on the list. There's -1/2. Okay, so yes, they're on the list. As far as rational roots, they should all be on the list. If they're irrational, of course they won't be on that list. But that was factorable. All right, let me pause before I do number 32. Hang on. Okay, here we go. Number 32. 3x cubed plus x squared minus 38x plus 24 equals 0. I won't expect any of these to factor by grouping. I'm looking at them. They clearly don't. Okay, so your p's over q's this time, factors of 24. We got 1, 2, 3, 4, 6, 8, 12, and 24. And then 3 are 1 and 3. So as a whole, your sets are those top ones. When we divide them by 1 or -1, whatever. See, that's the idea, right? It's the plus or minus for either set. Now, again, there are numbers, or there are values on here that can divide by 3 and reduce and such. Those are the ones that we ignore. It's the ones that we couldn't, and we write as a fraction. Plus or minus 1/3, plus or minus 2/3, 3/3 can, but 4/3, 8/3, 12/3 is 4, 24/3 is 8. Those are already on the list. So that is your whole list of possible rational roots. And we go to work on those. Doesn't look like 1 is going to work. Probably not -1. So I'm going to go to the graphing calculator one more time on that one. And there's that. And, you know, I'm hitting the moment of realization. This is number 32 of 65, right? We're not even halfway done. I'm 2 hours in. Even if I average 3 minutes a problem in this set, it's already a 3-hour video plus lecture stuff. I realize it's just going to be a long video. I mean, you don't have to do all the problems. Hopefully, knock on wood. I do, because I sadistically made a decision early on that I was going to do this kind of stuff. So there it is. All right, looks like -4 is one of the zeros. I didn't mean for that to happen, but it is. Let's see if there was a 0 before that. This may spoil the surprise by finding one, but let's see how long it would have had to have taken if I went to, oh, 3 is also a 0. So which one should I use for -4? I don't want to use both. I don't want to pretend like I found both of them. Let's use 3 in pretending like that was the first one that we found, okay? So, -4? What -4? I only found 3. So, apparently -4 is one of the answers, but we didn't know that. Okay, so let's use 3. Now, f of 3 equals 0, therefore using synthetic division, which I love. I love synthetic division. Oh my gosh. So much faster than long division for what we're doing here. 3, 9, 10, 30, -8, -24, and 0. Okay, so if 3 is a root, the next minus 3 is a factor. And this multiplies by 3x squared plus 10x minus 8. Okay. Hoping this is factorable. Well, it's going to be factorable, right? -4 was one of the roots, but as we work toward that factorization, see, now I wish I didn't know, because I know how we're going to write one of these. One's a positive, one's a negative, don't know yet which. Let's write them down. Factors of 8 are 8 and 1, 4 and 2, things like that. So we can try different things. Let's say we didn't actually know. We could try 8 and 1. That's -3 plus 8. That's 5. That doesn't work. Try 1 and 8. That's -24 plus 1. That doesn't work. Let's try 2 and 4. That's -12 plus 2. That's -10. I need +10. So if I need +10, I got to swap these signs like that. and that would get it, right? So if that's the case, then x either equals 3 or negative 4, as you saw. This one, we add 2, divide by 3, you get positive 2/3. Now, these were among your rational roots, including 2/3. You can see is right there. So there they are. Okay, let's move on to the next section where we find all real zeros of the function. That was asked before. This looks more the same. My guess is this one has some not irrational solutions as well. That's likely what's going to happen in these situations. All right, f of x equals. Now, all these are cubics. I don't know if it's worth stating now. It probably has more to do with the next section. But in any cubic, you must have at least one rational root. The other two may be conjugate pairs of irrational numbers or complex numbers, or they may be rational. But at least one of them must be. So it's not outside of your value of testing these to figure it out. All right, your p's and q's, because they're dividing by 1, so plus or minus factors of 60. 1, 2, 3, 4. Oh, I should write plus or minuses. I don't know. Some people might just wrap it around parentheses. I mean, if I did this, would you be hurt? Plus or minus 1, 2, 3, 4. Generally, I won't do this, but I already started. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 30 and 60. I think these were the numbers here, but all pluses and minuses, right? So there's the set. Okay, I think that's it. So, in testing values, I don't see 1 working here. Let me delete these other ones before I get started. So let's go straight into it. Graphing calculator. I think this may be one of the ones where they say, go and use the graphing calculator, if you heard me, if you saw the lecture portion. But they want to look at the graph. I want to look at the table. If they're insistent on graphing calculator, use graphing calculator however you may wish. Now, you don't need to do what I'm doing right here in the graphing calculator. It's just faster this way than always plugging in numbers into there. But you can do whatever you want with that. All right, let's try some. 1, negative 1, 2, negative 2. Go until you find 0. 3. All right, 3. So f of 3 equals 0, and this time it's actually appropriate to write f of 3 equals 0 because they give you an f of x. So 3 with 1, negative 2, negative 23, and 60. I don't really have much more to say on these problems until we get something kind of different. Hopefully it's been making a lot of sense what we've been doing, especially if you now know how things like synthetic division works and you know what it means to have a 0 remainder there. Here's your other polynomial factor. So x minus 3 is a factor. X squared plus x minus 20 is a factor. Basically, now it's just let him talk. He'll wear himself out. He's a little chatty. This factors into 5 and negative 4. There's really not much different in these problems so far. So far, this problem just rational solutions. We got 3, negative 5, and 4. It's just a brand new block until we find what I was kind of hoping for, to have some irrational solutions. They may still pop up. Not yet. All right, 34 at least is a different kind of question because it's the first time we see 3 terms in a cubic instead of 4 of them. Definitely rule out factoring by grouping in a state in a problem like this. But just keep in mind for synthetic division what you're going to have to pay attention to, which is make sure that you get your placeholder 0x squared in there. Anyway, it's not going to change how we go about things. This is your leading term. This is your constant. So factors of p over q, factors of 1 are just 1. So let's go straight into it. 1, 2, 3, and 4 can all divide by 8. 5 cannot. 6 can. Because that's 6 and 8. And that's where we start to get the other numbers. So 8 divided by 4 is 12. Divided by 3 is 16. Divided by 2 is 24. Divided by 1 is 48. I'd love to fit it on this line. So plus or minus 48. That's a lot. As you can see, the higher numbers are less likely to occur here. I mean, that's not true. It depends on what they want to do with the problem, but it looks like they're less likely to build problems with that in mind. So, don't expect them as much. Try some of the smaller numbers first. I can see 1 won't work. Actually, it looks like 2 works. I'm seeing that in my head. That you plug in 2, g of 2, without the calculator. This is 8 minus 56. Oh, not 2. Not 2. I thought this was going to work. Minus 48. Okay, maybe negative 2. Minus 48. So that doesn't work. Okay, g of negative 2. That's negative 8 plus 50. Here it is. Plus 56 minus 48. Okay, that's what I was looking for. So not that one, but this one. Okay. I was seeing the 8 in 48 with 56. Okay. So g of negative 2 works. No calculator. I didn't cheat. 1, 0, negative 28, and negative 48 on synthetic division. Zero remainder. Awesome. All right. X plus 2 is a factor. X squared minus 2x minus 24 is a factor. That is factorable into negative 6 and positive 4. And your solutions, therefore, will be negative 2, 6, and negative 4. Still no real difference as of yet. Let's see. Let's see. Someday, we'll get them. Number 35. What I see on number 35, I think this is the first time we're seeing it. I brought this up at one point. Perhaps it was the lecture. Perhaps it was another problem. Everything's positive. Which, although when we list p's over q's, sure, pluses and minuses are a portion of what you'd want to consider as roots. But here's the thing, guys. Positives will not be possible here. There's no way I can plug in a positive number and get 0 because it just goes further positive. So for me, all I care about are the negatives. I'm not going to write plus or minuses this time. I'm just going to write negatives. Now, there are a lot of factors of 3. This time I don't want to miss any. Negative 5, negative 6, negative 10, negative 15, negative 30. I don't even care. Whoops. I don't even care about the positives this time. Why test them if it's only going to get non-zero values? Who cares? Right? So that's just something I noticed. That's something that's of truth. If I try negative 1, that doesn't work. Okay, I'm going to just use the calculator. Negative 2 may work, but let's go to this guy. X cubed. I'm on a mental, mental exhaustion from trying numbers, and I don't want to make a mistake. So I'll show you that negative 1 shouldn't work there. Let's try negative 2. I should have just done with that. Okay, negative 2 will work. So g of 1 does not, or h of 1 did not equal 0, but h of negative 2 indeed does. So here we go. Sorry. Let's not be messy. Okay. With that first one being a factor, x plus 2, we also have x squared plus 8x plus 15 being a factor. That factors into x plus 3 times x plus 5. And you can tell that your 3 solutions here are negative 2, negative 3, and negative 5. Guess what? They would have been all the next ones in succession that would have been there. Just because I already have it on my graphing calculator, negative 3, negative 5, you would have hit the jackpot with all 3 of those. Nothing else would have worked, but they would have been there. Looks cool. All right, let's go on to number 36. We got f of x equals... Whoops. We got 36. All right, we have f of x equals x cubed minus 14x squared plus 55x minus 42. All right, haven't played with factors of 42 yet to my knowledge, but once again, with 1 being on the bottom, we just got to write those factors of 42 with plus or minuses involved. So we have 1, 2, 3, because 14, I believe. 14 and, yep. Not 4, not 5, 6 and 7. And then that's where we also hit that 14 and 21 and 42. 42. Okay. Does 1 work? 1 minus 14 is negative 13, plus 55 is 42, minus 42 is 0. I believe so. So f of 1 is 0. All right. So let's do 1 on synthetic division. Good to have small 1 every so often. I really do want to try and plug those in for myself. I just don't want to go down a list of 8 different ones and have it not be it. That's really the thing. I have a calculator for that reason. Okay, so x minus 1 times x squared minus 13x plus 42. I think we've seen this factorization. If not, I hope you know how that factors. That's x minus 6 times x minus 7. Maybe we haven't seen it. But x equals 1, 6, and 7. Apparently those are all positive. Didn't know to expect that, but hey, there they are. Still, once again, this set of problems, I fully expected some irrational solutions, not coming up. Now on this next set of 2 problems here, we do have to play with more of the q, factors of q coefficients. So, okay, there'll be a fraction answer somewhere, I guess. But I don't know if we have irrational solutions. No GCF, no factoring by grouping. We got p's over q's to still play with. Factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. Factors of 2 are 1 and 2. So let's write out that whole. Our possible factors are plus or minus 1, or divide these all by 1. What am I doing? I'm just counting up. There's no 5. So plus or minus 6, 9, 12, 18, and 36. I was going to realize I was going to go 7, 8, and like that wasn't going to work. And then divide them by 2, only the ones that give you fractions. So 1/2, only odd numbers pretty much. 1/2, 3 halves, and 9 halves. I think nothing else works. I think we've seen that list before, but just listing it out again. Okay. If I plug in 1, I get 2 minus 1. No, that's not going to work. -1, you get -2. That's not going to work. I'll try 2 and -2. After that, I'm going to give up and let the calculator do it. 8 times 2 is 16. Minus 4 is 12. Minus 54 is negative. No, that doesn't work. -2 is -8 times 2 is -16. Minus 4 is -20. Plus 54. Oh, hold on. -20 plus 54 is 34. Wait, what? Oh, never mind. That doesn't work. Okay. I don't think those ones worked there. So I think that would have given you like 80 or something. I think that's even worse. So I'm going to the calculator. That's enough mental checks. You can see that it's like, did you waste time trying to do ones for yourself? There's a push and pull. That's why I really like to just stop at 1 and -1, especially at 1. I'll test 1. I'm fine testing 1. It's a pretty quick calculation. After that, it's kind of maybe go for it. So just to confirm, just to confirm that these wouldn't have worked. All right, yeah, 70. Okay, 3 and 3 was the next one. You see, I could have finished by doing that one first before getting here. Oh, that is not an F. That is a P. P of 3 equals 0. Okay. Okay. Okay, so here we go. This is going to be x minus 3 times 2x squared plus 5x minus 12 equals 0. Once again, maybe it's factorable, maybe not. I don't know. We've only done that one solution. Let's try and test for factorization. 2x times x with something. Here we go. Factors of 12 are, let's start with 3 and 4. 3 and 4, one positive, one negative. We get -6 plus 4 doesn't work. You don't try 4 and 3. The reason is because, hold on, which way did I write it? Oh, hold on, that never would have worked. I wrote it the wrong way. You never should have tried this because no GCF. I'm sorry. Let's try it this way. You never try it with the way that would share a common factor here, like 2x plus 4. If that has a common factor and this didn't have a common factor, then you're doing it wrong. So let's try this one. -8 plus 3 is -5. I need +5, so I have the right numbers, just the wrong signs. I need this as a minus, this as a plus. Apologies for having what I had before. That never would have worked. All right, x equals 3 and 3 halves, if you add 3 divided by 2, and -4. So still rational solutions. They have not let up on any of those. There might be a whole nother problem set that has those, but not yet. Number 38, g of x equals 3x cubed minus 25x squared plus 58x minus 40. All right, what are the p's over q's here? Let's see if we can write out the list straight up, plus or minuses, just by understanding that we're going to divide these numbers by 1 and by 3. So dividing them by 1 are just straight up the factors. 1, 2, 4, 5, 8, 10, 20, and 40. Now divide them by 3, only ones that can't reduce, which I believe is all of them. So plus or minus 1/3, 2/3, 4/3. Yikes. Actually, let's do this. I'm going to cheat a little bit. Hold on. Oh, shoot, it kept the plus or minus there. Give me 1 second. It would have been a lot faster for me to just write it. I kind of just ran out of inspiration. Here's the thing. We write these so we know what to test with, right? It's likely, very, very likely that you hit it before you get to this stage. So how much value is there in actually writing all of these? Depends on what you're asked to do by your own teacher, by the book, what you feel comfortable with. Me, I'm kind of comfortable going without it all. I know to test 1 and 2 and things like that, and I feel like I'm going to find one before it hits something. There are times where I haven't, and I had to wait till I get to the fractions. I don't feel like this is among those problems. But how much is it worth it for you to do all of those? I don't know. That's a lot of numbers. 1, 2, 3, 4, 5, 6, 7, 8 times 2 times 2. 32. There are 32 different possibilities, and writing all those would take a while. So I tried to my way through. My way through. All right, so I have 3x cubed minus 25x squared plus 58x minus 40. I didn't actually bother testing 1 and negative 1. It might have worked. Let's see. 1, negative 1. Whoops. I keep just hitting negative. Negative 1. Okay, those didn't work. I feel better. 2 works. Okay. Yeah, right? Why am I listing the whole thing when, like, that's what I might try in the future of, like, try them until I kind of go, like, nothing's working. Let's list them out. Maybe if you feel better now about how the listing works, maybe I won't go with listing them unless they ask it. Sound good? I'm already at, like, 2 hours, 20 minutes. So at some point, we got to just bite the bullet and try some things that'll save my poor little hand and my time. All right. So 2. And poor you guys if you truly have to use synthetic division on all these. The book is sadistic when it works out things like that and forces that on you. Okay, so this factors into x minus 2 times 3x squared minus 19x plus 20. And if history is an indication of anything, then this is factorable. So let's try it. 3x and x, both negatives. Let's try 5 and 4 to start with. I think I already see it. 5 and 4. Negative 15 minus 4 is negative 19. That seems to work out. So x equals 2. X equals 4/3. Add 4 divided by 3. And x equals 5. Those are the ones. Okay. Let's move to numbers 39 and 40. Use the graph to shorten the list of possible rational zeros of functions. Then find all real zeros of the function. So they're not asking you to use the graphing calculator for it, but they do have the graph, right? So instead of me necessarily typing that out in the graphing calculator, I'm going to take one of these and kind of do what they're stating with it, what they stated before. I just don't want to do it on a graphing calculator. So here's what we're going to do here. 4x cubed minus 20x plus 16. First thing I want to do personally is factor out this 4. Well, here's the thing, right? We're trying to find zeros. Let's set this equal to 0 to begin with. I'll factor out the 4 meanwhile. But I have x cubed minus 5x plus 4 equals 0. Please don't confuse this with x squared minus 5x plus 4, which is factorable. I will divide by 4 along the way. So I'm basically getting rid of the 4. I don't need the 4 for my solutions. I just need this guy right here. So when it comes to my coefficients, synthetic division, testing numbers, things like that, I can test right here. Now, it says, use the graph to shorten the list of possible rational zeros. Now, my possible rational zeros would include plus or minus 1, plus or minus 2, plus or minus 4. I could try and test them, but they do say use the graph. My graph does show it looks like it crosses at x equals 1. I believe that it does. So I'm going to go ahead and try that. F of 1 is, and I can use this 1 right here. I'd still get the same 0. I know I already wrote set equal to 0. Maybe I shouldn't have. Let's actually leave that till later. Let's still write f of x equals as far as us testing. But I don't care about the 4. Shoot. I have to save the 4 till later. I factored, right? But I don't care about the 4 for the thing. 4 times what? Right here, right? 1 cubed minus 5 is negative 4 plus 4 is 0. So f of 1 is 0. I don't care about the 4 for anything else here on out. Got it? That includes synthetic division. I got a 1. I got a 0x squared. I got a negative 5x and a positive 4. And we go to work on it. And we end up getting this here. So we get f of x equals, as a whole, actually, now I'm going to set it equal to 0. But I have 4 times x minus 1 times x squared plus x minus 4 equals 0. So again, I don't care about the 4 with this because in zero product property, 4 can't equal 0. Only x minus 1 could equal 0, so x can equal 1. Or x squared plus x minus 4 equals 0. Now, this seems to be the first among the problems where you have irrational solutions. This is one where I'd love to use quadratic formula or something like that. As you look at the other zeros, you're saying, hey, maybe negative 3.5 is one of them. Hey, maybe this 1.5 is one of them. Well, tell you what, that wasn't possible in the first place. Your p's over q's, whether I looked at the one with the 4 factored out or not, let's factor the 4 out. The p's over q possibility was just plus or minus 1, 2, and 4. They were only integers. So these were the possible rational solutions. 1 is the only one that's actually rational. The other ones are not rational. There is no 1.5. There is no negative 3.5. The answers are close to it, and we're going to find them here. We got to use quadratic formula. So I'm going to evaluate using the discriminant first, b squared minus 4ac. That's my personal go-to, b squared minus 4ac. And that equals 1 plus 16, which is 17. That's the guy in the square root. So we're going to get x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times 1, 2a. And those are the two other answers. So it's these answers here and that answer there. Now, I think that the book did show the rounding of these. I'm not generally going to do it. They didn't ask me to round, but I want to show you that these numbers, negative 1 plus root 17 over 2 and negative 1 minus root 17 over 2, are apparently pretty close to negative. I kept saying negative 3.5. I meant negative 2.5. I saw the negative 4 here. Are really close to negative 2.5 and positive 1.5. Apparently, it's close to those things. Let's see if that's a for sure. So if I go to the calculator, I don't care about the graphing on this thing. I just care about, let's do negative 1 plus root 17. Divide that by 2. There's the 1.5-ish number. And then let's do negative 1 minus root 17 divided by 2. This is going to be the negative 2.5-ish number. The decimals are the same there, but that's what they round to about, and that's where those ones came to be. So 1 was the only rational solution. These were the irrationals. That's our first go at those ones. And it's probably only one of 2 goes that we have at this, because number 40 seems like the only other question like this that has it. So number 40. Number 40, we have f of x equals 4x cubed minus 49x minus 60. No common factor this time. So this time we're going to have to deal with your p's over q's the way that they are. However, we have the graph to play with, and that's really what I'm just going to do here. My graph seems to indicate that 1, 2, 3, 4 is a rational root of this. I want to test that for sure and see if it works, whether you plug in 4 into here or go straight to synthetic division. This time I'll go straight to synthetic division just because those numbers are bigger. 4x cubed plus 0x squared minus 49x minus 60. And I trust it's a rational root. And I trust that these are irrational. I don't know that for sure. We'll see what happens after this one. We'll break it down to a quadratic and see how to solve. So we get 16 and 64 and 60. Yes, so 4 is a rational root of this. That checks out. So this now factors into x minus 4 times 4x squared plus 16x plus 15 equals 0. I can test for factorization. I don't know if it will pan out. I don't know if it's worth testing after we saw the other one was irrational. I'll try it very quickly here. If it is, it would be a 2x and 2x. If you've had me before for some stuff, you'd know why that would be the case. We can try 3 and 5 and 15 and 1. If they don't work, we'll leave it. This actually works. This is actually factorable. This is 10 plus 6, which is 16. I didn't actually expect it to be factorable. And so, okay, so that's x minus 4 equals 0. So therefore, x equals 4 and negative 3 halves and negative 5 halves. So those numbers are actually negative 1.5 and negative 2.5. Do they look like they're on negative 1.5, negative 2.5? I'd say so. Did I know for sure? Absolutely not. No, I had no idea. But they are, and those are the solutions. Whereas this one had quadratic solutions, and I want to be sure I did the problem right. I believe I did. But whereas the other one had quadratic solutions, this one had rational solutions once again. So it said use the graph to shorten the list of possible rational zeros. I don't know if they actually meant write out what they think it could have been. So, with this one, I suppose we could have said, hey, negative 1.5, negative 2.5 were possible because negative 3 halves is among, I guess, the factors here, because 3 is a factor of 60, 2 is a factor of 4. 5 is also a factor of 60 for negative 5 halves. So, yeah, maybe I didn't do the instruction perfectly right, but I did use the graph to get the answers. Okay. 41 to 46, write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. So on number 41, they're going to be as decent as possible for you. These are the zeros we're going to be using. If we have these zeros, that means your factors are x plus 2. And we write this in f of x form. But we have x plus 2 times x minus 3 times x minus 6. It's the opposites, right? We've spent so long on zero product property, we should be able to go opposite of this now. They said write it, of least degree. This is the least degree, meaning don't add more x's that shouldn't be there. So this is a cubic. They do want you to expand this, though, in standard form. So treat any 2 at a time. I'm going to expand x minus 3. I'm going to FOIL x minus 3 times x minus 6 into this guy. And then we'll keep going on that. So x times these 3 is x cubed minus 9x squared plus 18x. 2 times these 3 is 2x squared minus 18x plus 36. And when you combine everything, you get x cubed minus 7x squared. 18x minus 18x is 0, so plus 36. And we could go back and do rational root theorem, test this out, and find out these are the roots, use synthetic division, all that. Obviously, we're not going to. But, or you could plug in negative 2 into here and get 0, plug 3 and get 0, plug 6 and get 0, if I did the problem right. And that would be it. All right, number 42. Looks like I'm ready for the next page. Number 42. Negative 4, negative 2, and 5 lead us to x plus 4, x plus 2, and x minus 5 as the things here. By the way, they did mention the leading coefficient's 1, so I'm just ignoring that instruction as a whole. I'd put a 1 there, multiply by everything, and it goes away. So if this had leading coefficient's 2, I would save it till the end when it comes to distribution. I would simplify everything here, then distribute the 2. But it said 1, leave it. All right, expand and go. No different from the last problem. I expect to get some problems here that are different because of the examples that they showed before. So get ready for those. Anyway, this expands to that. And now we continue on. We do x times those 3. So x cubed minus 3x squared minus 10x. And then 4 times those 3. 4x squared minus 12x minus 40. So combining like terms, we do get our cubic. That's our least degree. Negative 3x squared plus 4x squared is 1x squared. Negative 10x minus 12x is here. And negative 40 doesn't combine with anything. That is our polynomial cubic. I'm good. Now, these ones are where we start to hit some, conjugates. Irrational solutions, and they always come in conjugate pairs. They said we need rational coefficients in the end, and that's going to come in play here. So negative 2 and 1 plus root 7 are among our rational solutions. Now another one would have to be real solutions. 1 minus root 7 would have to be another one. They must come in conjugate pairs for us to be able to have rational coefficients when we multiply everything out. So our f of x this time will be x plus 2 times, and here's how they kind of did it in the book. This is a fair way to do it. I want you to recognize it. We're going to subtract 1 plus root 7, so x minus 1 plus root 7, and then we're going to subtract 1 minus root 7 like that. Now, an in-betweener here is we can distribute that negative, and then we'll have x minus 1 minus root 7 and x minus 1 plus root 7. So kind of a swap of those things there. You could do this whole like multiply this out, trinomial times trinomial, but it would take quite a bit of time. So what the book does instead is they say group the x minus 1s together because it's the same on both of these. Treat these kind of like an a. This ends up being a difference of two squares result. You have an a minus b times an a plus b. And a minus b times a plus b distributes to become a squared minus b squared. So when you end up getting that into what you want it to be, this would be a squared minus b squared. That's a root 7. Root 7 squared is actually 7, so let me just write that. X minus 1 squared minus 7. Voila, everything's now rational. And that was only possible having a conjugate in play there. Now, we're still not done with this as a whole, but that cleans up that portion of what we need to do. So that's the way that the book kind of goes about it, and that's a great way of doing it. I'm never going to stop someone from doing that. I do want to show you an alternative that works. You still get to the same thing. You get to this part, kind of in probably faster fashion, but there's the one that the book kind of showed. Anyway, this is now minus 6. So let's do this expansion now. Multiply x by those 3. Multiply 2 by those 3. And as far as all full work shown, which this looks glorious, negative 2x squared plus 2x squared is 0. Negative 6x minus 4x is here. And there's negative 12. So this is all rational coefficients, leading coefficient of 1. Least degree. Least degree is a cubic. We can't make this a quadratic and have rational coefficients. So the cubic was the least degree we could possibly have. There it is. All right. Number 44, let me show you that alternative take, and let's see how much fewer steps it will be. And I'm going to introduce it by showing out of these. Recall how this thing works as a whole, right? This whole, if x equals 4, then x minus 4 equals 0, that kind of thing, and therefore x minus 4 is your factor. You can do something with this one as well in the same light. If x equals 6 minus root 7, then x minus 6 equals negative root 7. And if I square both sides right now, squared, then you actually get your conjugate pairs taken care of. Because here's the thing. If 6 minus root 7 was one of them, 6 plus root 7 is one of them. But if I take positive or negative root 7 and square it, then this becomes x squared minus 12x plus 36 equals 7. Doesn't matter whether you square the positive or negative, squaring that gets you that result. Subtract the 7 over, you get x squared minus 12x plus 29 equals 0. Therefore, this is the other factor. When set equal to 0, not the other factor, it's two factors in one combined. X minus 4 is one of them, and this is one of them. So that result here, like I said, I could write the same thing here. X minus 4 equals, x equals 4. Therefore, x minus 4 equals 0. Therefore, this is the other factor, right? So as a whole, that would become f of x equals x minus 4 times x squared minus 12x plus 29. Now, if you use the other method, you'd be getting to the same thing. You'd start off by writing them with factors inside like this. It gets a little wonky and such. You got to use difference of two squares to get it in there. But that squaring result is the same thing that I got right here when combining like terms. I've taken care of both conjugate pairs with that. You do need to identify whether or not you do the squaring thing. It's best that you identify what the other conjugate pair is. You do not want to leave that out, even if squaring takes care of it without it. But that's another way of going about it cleanly. I believe it's quicker than the other method. I'll use both methods separately again on numbers 45 and 46, so you can kind of judge for yourself which one you prefer. Oh, whoops, I got to distribute. So right here, x distributes here, x cubed. And negative 4 distributes here, Be careful, change your signs. Plus 48x minus 126. No, 116. So, this is where my back and neck kind of start to kind of hurt. 29 plus 48 is 77. And yeah, those were bigger numbers for sure, for sure. But yeah, you have some conjugate pairs there. For sure, for sure. Okay, number 45. Let's go back to the method that they chose. Now, 0 is one of our zeros. We've seen a lot of zeros. We've seen 0 as our 0 multiple times when we did graphs. Remember, one factor is going to be, oh, well, keep this in mind. We will also have 3 plus root 5, okay? So as a whole, f of x equals, I'm going to write the 0 first. X equals 0 means x is one of your factors, means it's a common factor. Now, x plus 6 is one of them. And if you notice from the last time, if we subtract 3 minus root 5 and 3 plus root 5, we'd have parentheses there. So distributing the negative means that will be there. And this one, distribute the negative into here, will be 3 minus root 5 like that. So I'm going to write it like that to get us going. Let's get into our difference of two squares as well. Straight up like that. Maybe this saves time as a whole doing it like that. If you can skip steps making that happen, great. You got to notice that. A plus b times a minus b is going to be a squared minus root 5 squared is 5b squared. And then that guy expands to, you know what? Let's distribute these right now. X times x plus 6 is x squared plus 6x. Let's get that going. And then over here I have x squared minus 6x plus 9 minus 5. Wish my handwriting wasn't so poor. X squared plus 6x. And this is x squared minus 6x plus 4. I kind of regret distributing the x first. I like to see the factored form version of this when it's as clean as possible. But it doesn't change what we're going to do here. Once we distribute, we get x to the 4th minus 6x cubed plus 4x squared plus 6x cubed, those cancel, minus 36x squared plus 24x. There's going to be no constant term this time because x was a common factor, so the least degree term will have an x in it, unless it cancels, which it shouldn't. X to the 4th, negative 6x cubed plus 6x cubed is 0. 4x squared minus 36x squared is negative 32x squared, and then plus 24x. That's our standard form. I don't know if there's something canceling so often, if that was them being clever, or if that should happen as often as we've seen it. But it's happened quite a bit already. And again, that's least degree. The smallest number of zeros we can get is 4, given that we need a conjugate pair. A conjugate pair. All right, number 46. Our zeros are 0, 5, and negative 5 plus root 8. Now that also means negative 5 minus root 8 is one of them. So let me go to my version that I showed you before. If x equals negative 5 plus or minus root 8, let's add 5 to this side. And let's square both sides now so we can take care of that. See, the reason to add that over to that side is because squaring this now will bust that radical. So now this is going to become x plus 5 quantity squared equals 8, or x plus 5 quantity squared minus 8 equals 0. So this is that other fact. Oh, sorry, I should totally expand that thing. I should have done that a while back. Let's do that again. X squared plus 10x plus 25 equals 8. So x squared plus 10x plus 17 equals 0. So this would be the other factor that we're talking about alongside the factor that is x and x minus 5. So as we bring this guy down here, our f of x will equal x times x minus 5 times x squared plus 10x plus 17. Okay, so that's the whole of that one. That includes both conjugate pairs. That's what made that thing clean up the way that it does. F of x equals, now let's start the distribution. This time I'll leave the x on the outside as we work the inside, and then we'll increase it. So I got x cubed plus 10x squared plus 17x minus 5x squared minus 50x minus 85. Now we have two things to do. We have to combine like terms and increase the degree by 1. Let's see if we can do both together. X times x cubed. 10x squared minus 5x squared is 5x squared. Well, so let's make it 5x cubed. let's see, 17x minus 50x is negative 33x, so negative 33x squared, and then the minus 85x stands alone as its final term, no constant term, and there's number 46. Okay, number 47, comparing methods. Solve the equation using two different methods. With which method do you prefer? Explain your reasoning. I can tell you how those methods will go. I can tell you which method I prefer right now. X cubed minus 4x squared minus 9x plus 36 equals 0. Kind of have two options to go off of here. Factoring by grouping, which is possible, or rational root theorem, which of course should be possible with that as well. Factoring by grouping. Factoring by grouping is a method. Okay, so we can factor out x squared from the first two terms to get x minus 4. We can factor negative 9 out of the last two terms to get x minus 4. This factors into x squared minus 9 times x minus 4, or x minus 3 times x plus 3 times x minus 4, when equal to 0, zero product property, x equals 3, negative 3, and 4. There's the factoring by grouping method, my preference. Now, the other method, rational root theorem. Worst method ever. Not really. P's over Q's, if you were to actually test them out, coefficients, 36, factors of 36 divided by factors of 1. So plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36. We test those ones. So let's pretend like we didn't know that these ones existed. I probably should have done the rational root theorem first to not reveal those. But listen, you plug them in, you try some ones. 1 and negative 1 won't work. 2 and negative 2 won't work. 3 will work. So if 3 works, if that f of 3 equals 0 works, we then use rational root theorem on this guy right here. And we get 1, 3, negative 1, negative 3, negative 12, negative 36, and 0. So this factors into x minus 3 times x squared minus x minus 12 equals 0. X squared minus x minus 12 factors into x minus 4 times x plus 3. And we finally get our solutions of 3, 4, and negative 3. Did we get the same answers before? Yep, just wrote them in different order there. So there's rational root theorem, there's factoring by grouping. Now the one saving grace for me that I did was I said, well, I already knew these values were there. I'll save myself calculator time. But in reality, if you started with this option or you didn't know that option or whatever else, you would have had to test 1 and negative 1, 2 and negative 2, or whichever order you want to choose before finding out that 3 works. So that would have even taken longer. Doesn't look like significantly extra work. Remember, you don't have to list your roots. You know that if you know your factors, you're good to go. They say, which method do you prefer? Explain your reasoning. Clearly, I prefer factoring by grouping. I think most people would. But you have to know you have factoring by grouping to work. By grouping, because it's quicker. However, not every problem is factorable by grouping. I'm telling this to you guys. By grouping, so you must know both methods. Prepare yourself for both methods. That's basically just a little public service announcement. Prepare yourself. Because we saw a lot where rational root theorem was really the only way to go. But that's our first instance of, well, they said do both. And tell me. Tell me which one you officially like. Is it possible for a cubic function to have more than 3 real zeros? Explain. Well, this is something I think that the next section is going to dive into as a whole. I've already mentioned this several times that at most it can only have 3. So the answer is no. No. Because a cubic function, now here's kind of a reason besides just saying that it works. A cubic function can at most only, well, that was going to say the same thing again, but you can only break up your x cubed into 3 factors of x, have 3 factors, whether rational or not, real or not, rational, real or not, meaning at most only 3 solutions can be had. I don't know. I don't know if I have the best explanation for that, but just the idea is that in a cubic, also when it comes to turnarounds and things like that, which is probably, we're probably explaining it backwards, meaning only 3 solutions means at most you can only turn it around 3 times, twice I should say. But that's the number of turnarounds you can only get in a cubic at most. Therefore, it can only have those many intercepts. That's kind of a weird way to talk about it, but that also explains how those things work. Now, you can have less. It's possible to have less for a couple reasons. You can have 2 imaginary solutions. You can have a solution with a multiplicity of 2. You can have all 3. You can have 1 solution with a multiplicity of 3. So it's possible to have less in some scenarios, right? This graph can be up like that. This graph can be up like that. All those kinds of things are also possible. Okay. Now, like I said, I believe the next section really takes that as a whole and wants you to do a lot more with it. Number 49, word problem. At a factory, molten glass is poured into molds to make paperweights. Each mold is a rectangular prism with a height of 3 centimeters, with a height 3 centimeters greater than the length of each side of its square base. Each mold holds 112 cubic centimeters of glass. What are the dimensions of the mold? So if I have volume is, area of base times height, or length times width times height. Your length equals your width. They're both the same. They said it's a square base, so I'll just call those x's. Your height is going to be 3 more than either of these, 3 centimeters greater than the length of each side of the square base, so x plus 3. So you're looking at something, you don't need the drawing, but if you're looking at something like this, it's 3 centimeters taller than either of those things to make the paperweight. Sure, like that. But this is x plus 3. Now, the volume also equals 112. So when we multiply x with x and x plus 3, we are getting 112. This is what are the dimensions of the mold. We must solve for x now. This may be factored, but if it's not set equal to 0, then you can't solve this using zero product property until it's set equal to 0. That means you have to expand this first. X times x is x squared. Subtract the 112 over as well. Distribute this one more time. X cubed plus 3x squared minus 112 equals 0. And we have to solve. Now, clearly, this is one of those instances where you can't solve by, it's not a quadratic. There's no common factor. Factoring by groupings out of the picture. So this is rational root theorem time. A rational root must exist among the setup. We got to figure out what our rational roots are. Remember, factors of 112 over factors of 1. We can divide it by 1 and get 112. I'm going to try and go this way with it. Divide it by 2 and get 56. Divide it by, 4 and get 28. Can't divide by 6. Divide it by 7 and get 16. Divide by 8. Is this the right list? I want to make sure it's the right list. Here's the thing. So on and so forth, right? Let me test these ones first and see, because I might have skipped one. I don't know if I might have or not. But let's test these ones first and see if we run into one. If we do, I don't care about the rest of the list. But rational root theorem is the idea, right? All your factors of 112. 112 is kind of a weird number. I normally don't play with it. So I'm going to go to the graphing calculator straight up, guys, right now. I'm going to type in x cubed plus 3x squared minus 112 into my graphing calculator. So I'm going into that. I'm going to substitute in some values. 1, -1, and 2 don't work. Let's try -2, 3. Oh, not 3. 4. 4 works. So the rest of the list don't really matter to me because 4 is one of those factors. Okay, so if 4 is one of the factors, then we'll use 1x cubed, 3x squared, 0x, -112. Do synthetic division on this guy. I'm guessing 4 would have to be the answer, though. I'll talk about why in a moment. But maybe there's more than one answer, but I'll talk about why this... Well, I think 4 is the only answer. If these are different kinds of solutions here. But anyway, we get 1 here. 4, 7... 28, and 4 times 28 is 112. So here you get x minus 4 times x squared plus 7x plus 28. So this is one of those instances where, this one's not factorable, okay? Not only that, but it doesn't have real solutions. If you go into this one, you just go to the discriminant, right? Set this equal to 0, solve using quadratic formula. You get b squared minus 4ac. We just saw that 4 times 28 is 112. This is a negative number, negative 73. So no real solutions there. I'm not going to get into the imaginary solutions. That doesn't matter for our case of what we're doing, right? We don't care about those. Just x equals 4 is the only one that we care about for that set. The imaginaries, no. Once I saw the rational solution, that should have worked. I don't see how another one really would be possible after that. So if x equals 4 works, then what are the dimensions? Your dimensions, and they're in centimeters, your dimensions are 4 centimeters by 4 centimeters by the height is 3 centimeters more, 7 centimeters. So 4 times 4 is 16. 16 times 7 is 112. And it works. Okay, number 50. Mathematical connections. The volume of the cube shown is 8 cubic centimeters. Write a polynomial equation you can use to find the value of x. All right, so 50. Part A. Given the cube that we have, and it is a cube, we have x minus 3 quantity cubed, and that gives us 8. It says write a polynomial you can use to find the value of x. I guess that would be the start of it. I don't know if they want standard form. Even though the answer, the answer may be 5. Don't go straight into the whole taking cube root of both sides, even though I think that that's how it kind of works out here. I would just be careful on those. I wouldn't say, I don't know. That is the answer, but I'm not going to speak on as to why. Let's do what they're talking about. So as far as their polynomial business, let's expand this cubic. This is 1x cubed minus 3 times x squared times 3 to the first plus 3 times x times 3 squared minus 3 cubed, and that equals 8. So x cubed minus 9x squared plus 27x, hey, we've seen this before, minus 27 equals 8, and now we can subtract that thing over. X cubed minus 9x squared plus 27x minus 35 equals 0. So write a polynomial equation used to find the value of x. This is it. I don't know if we were supposed to set it equal to 0 yet. This could be an f of x equals, but basically that's the polynomial equation we can use in that way. Identify the possible rational solutions of the equation in part A. Again, it probably should say f of x equals, but I got it into this scenario because of what we were doing on it. So I'll just go and treat it like that anyway. So your possible rationals are factors of 35 over factors of 1. So part B, we actually have to list them this time, and there aren't many. Plus or minus 1, 5, 7, and 35. Now I'm anticipating 5 is the answer here. Use synthetic division to find a rational solution of the equation. Show that no other real solutions exist. And I think that's really the big part. This time they did say use synthetic division. Now 5 will be the value here, but let's test 1. Because this time they did say use synthetic division. So I'm playing dumb on that one and said, they're going to force it on me. Let's go at it. So 1, negative 8, 19, and not 0. Negative 16. Negative 16, no good. Let's try negative 1. Also should be no good. We get 1. Negative 1, negative 10. 37. Ooh, close. Oh, never mind, not close. Negative 72. No 0 remainder. And we try 5. 5 should go. 1, negative 9, 27, negative 35. Okay, 1, negative 4, 7, and whoops, 7. Hold on. Timeout. 7 and 0. Okay, so 5 works out. Now, they stated, I gotta kind of move these things up here a little bit. Sorry. I want to use this side over here. They stated, show that no other real solutions exist. So we found the rational one. So that means that this factors into, x squared minus 4x plus 7. So this is x minus 5 times x squared minus 4x plus 7 equals 0. So, I think that was kind of the same as the other problem, right? So x equals 5 is one of them. We already know that. But with this one right here, not factorable, and show that no other rational solutions exist, or real solutions exist, we do the discriminant. We do b squared minus 4ac. And what we get here is 16 minus 28, which is negative 12. And that's what shows no other real solutions exist. No real solutions. So what are the dimensions of the cube? So now that we have what we have, sorry, kind of running out of space here. So with part D, because x equals 5, the dimensions of the cube are 5 minus 2 times 5 minus 2 times 5 minus 2. So 2 by 2 by 2. 2 centimeters by 2 centimeters by 2 centimeters. Now, I'm jumping back and forth in how I was saying don't just automatically take the cube root of both sides, but it depends on what you're trying to do. If you're trying to find your one rational solution, I suppose you could. If you're trying to find all solutions, including those imaginary solutions here, you wouldn't do that. You would actually have to find them by doing everything we just did, right? So there would be more to do in that sense. Okay, number 51. Problem solving. Archaeologists discovered a huge hydraulic concrete block at the ruins of Caesarea with a volume of 945 cubic meters. The block is, so volume is 945, and it's a block. The block is x meters high by 12x minus 15 meters long by 12x minus 21 meters wide. What are the dimensions of the block? So our volume also can be expressed with that x by 12x minus 15 by 12x minus 21. What are the dimensions of the block? We're going to have to solve for, not 0, equals 945. We're going to have to set it equal to 0 eventually with this, right? I almost want to get the common factors out and put them back in when we're done, but I guess I'll just deal with what we have here. Let's first try and FOIL this out. We get 144x squared minus 252x. Let's just write this. Minus 180x. There should be an x there. Plus 315. I hope I'm doing that right. I'm doing that in my head. Equals 945. I think that's 315. So this is x. Let's distribute the x into there as we combine like terms. 144x cubed minus, now this is negative 432, I think, x squared plus 315x. Let's subtract the 945 over as well, equals 0. These, you can divide these all by 3 at least. I think you can divide them all by 9. Maybe something even bigger. If I factor a 9 out of here, I get 16x cubed minus, I'm going to do this in my calculator, 432, whoopsie, wrong screen. 432 divided by 9. There might be a bigger number than even 9. 48, ooh, there might be a bigger number. 48x. Oh, you know what? We spoke on the common factor. Why didn't I figure that out? Okay, you know what it is? Factor 3 out of there. Factor 3 out of there. Oh, it might just be 9 then. 315 divided by 9. You know, I should have just factored out the stupid factor. Yeah, 35. Plus 35x minus, and that'll be 105. All right, so getting that factor out of there, I think that's as much as I can reduce it, which is important for what we have. Now, this is factorable by grouping. So that 9, listen, I'm gonna get rid of the 9. I don't need it. This is a squared, by the way. This is factorable by grouping. I can factor 16x squared out of these two, I get x minus 3. I can factor a 35 out of these two, I get x minus 3. You might be wondering at this stage, how can I tell something's factorable by grouping? It has to do with proportionality. 48 is 3 times larger than 16. 105 is 3 times larger than 35. I can see those ones in my head more. That part matters for this part, clearly, because the 3's need to be here. You know, that's an important aspect of it. That's a lot of what it has to do with, and the signs are in agreement. It's just something that I recognize a lot when doing those ones. Anyway, so we do get 16x squared plus 35 times x minus 3 equals 0. Now, This part has no real solutions. You could ignore that one straight up. This is x equals 3. That's going to be the only answer that matters to us. These have imaginary solutions. If you're curious on them, because this, I don't need quadratic formula for this one, I can subtract 35, divide by 16, and take the square root of both sides. If you remember how these work, it's x equals plus or minus I times root 35 all over 4. Those would be the other ones. We don't care about those ones, though, as they're imaginary. So 3 is the value for x that we get, and the question is, what are the dimensions of the block? So the dimensions of the block are, we have a height of 3 meters. We have a length, I was going to say a long, we have a length of 36 minus 15, 12 times 3 minus 15 is 21 meters, and we have a width of 36 minus 21, which is 15 meters. 3 times 21 is 63, 63 times 15, double check that, 63 times 15 is 945. Could have you solved with rational root theorem? Absolutely. Can I factor by grouping? Absolutely. So I'm going to use that one. All right, number 52. Making an argument. Your friend has been right once this chapter. Hasn't been right, I think, all last chapter. Come on, friend. Let's go. Your friend claims that when a polynomial function has a leading coefficient of 1 and the coefficients are all integers, every possible rational 0 is an integer. Is your friend correct? Explain your reasoning. Yes. If you've noticed, well, we can kind of say it here. My friend is correct. Good. My friend is correct. When we consider our p's over q's, p over q possible rational roots, q represents all factors of the leading coefficient. If your leading coefficient is 1, the only possible factor is 1. I mean negative 1 as well. I'm not really talking about that. The only possible factor is 1. And dividing an integer by 1, remember the other factors. Dividing the other factors, the factors of q, or of p by 1, would lead to only integer possibilities. So good. The friend is back. The friend is back and at it for at least one of these. Go, friend. You go. My friend is Glenn Coco. You go, Glenn Coco. Number 53. Modeling with mathematics. To me, that generally sounds like use a calculator. When I see these numbers, I'm thinking use a calculator. During a 10-year period, the amount in millions of dollars of athletic equipment E sold domestically can be modeled by that big guy. Write a polynomial equation to find the year when about 24 billion something of athletic equipment is sold. Okay. So we start with E of t equals, and we have this guy, negative 20t cubed plus 252t squared minus 2. Okay, we're going to set this equal to that. Now, this is in millions of dollars. So the important aspect of this is 24 billion, 14 million is equal to 24014 million, because that's in millions of dollars. So there's a unit conversion right there. We got to turn our number into this. So when we work on this problem, we are going to set this equal not to 24 something billion, but just that number right there. So this plus this minus this plus this, I know that's very descriptive, equals this. There's this video online, I think for some reason, I don't know why it's titled it. I think it's titled John Mayer Hates Baseball. And I think they're pretending like John Mayer's commentating. Maybe he is, I don't know. But he's doing a play-by-play thing. He's like, and this guy steps up to the plate, and then a pitch is thrown. He goes, and that happened. I'm just like, this plus this minus this. All right, first things first, I'm going to set this thing equal to 0. I'm truly seeing some common factor bits. Can I do this as well? We'll do common factors eventually, but I want to factor out a negative eventually. This is a lot of numbers to write. Minus 280t minus, I wanted to go without the calculator, but here I don't want to mess up the subtraction. 216, I won't truly be able to go without the calculator unless it's factorable by grouping. 014, negative 2400. Oh, that's a clean number. Negative 2400 equals 0. Now, this can't unfortunately be factorable by grouping, because even if this times something is that number, this time something is that number, which it's not. These are both negatives, and while those have opposite signs. Now, I'd love to change the signs, and I'd love to get a common factor out of this even still. I can't, unfortunately, factor out 20 because the 252. Best I can probably do is 2. Or 4, at least, maybe 8. Does 252 divide by 8? Oh, 20 doesn't divide by 8. Let's try 4. Negative 4, if you will. If I factor negative 4 out, I get 5t cubed. I'm just playing with the problem right now, if that's cool. Minus, 63. Minus 63t squared. Yeah, no common factors there. Plus 70t plus 600. So that negative 4 means nothing to me anymore, right? Assuming I've done everything right so far, I'll just kind of wipe it out. Now we're going to talk about our p's over q's and find our probably 1 value of t. Now p's over q's here, we have factors of 600 divided by factors of 5. Factors of 5 are 1 and 5. 600 is way too many factors, right? We're doing 1, 2, 3, 100, 200, 300. I mean, this list will go on quite a while. There's really no... there's no 7 or 8 or 9, but there's 10, but it keeps going like that, quite a few. We can divide these numbers all by 5. 5 divided by 5 is 1. 10 divided by 5 is 2. We'll leave them. But let's find our first one here. Because it's not, factorable by grouping, we got to kind of use rational root theorem. So I'm going to plug this one in the calculator from what we have here. Get that started. I have 5x cubed minus 63x squared. I hope I didn't mess any of those up. Plus 70x plus 600. So let's go and try some of these numbers out. None of those worked. Let's try negative 4, because I doubled that up. 5. Aha, 5. So, right, we don't have to write a whole list, but we have to try some until they work. I bet they would have asked you to use the graph, the graphing calculator thing, right? That we could look at this thing on the graph, find out where it crosses there. That actually would have been reasonable. You see right there where it crosses? I think that one would have been fine to do. That's probably what the lecture portion of the video would have preached, and there's that. Now, I'm not looking at the entirety of the graph, right? There's a lot more this thing does. It clearly goes back up as well as a cubic. If you want to see that zoomed out, you can. In which case, let's zoom out just a little bit. Let's do an x value of like 20 and see what the heck was going on that side. All the window, this is a crazy window range if you keep in mind, and it does that. Is that a rational number? Maybe. I don't know. So let's try. Let's go back to this. 5 was a rational root, so let's do that on synthetic division with synthetic division on this. We have 5, negative 63, 70, and 600. And we got our 5s, our 25s, our negative 38s, our negative 190s, our negative 120s, and negative 600s and zeros. Okay. Still a weird kind of thing remaining there, and I do wonder if this is rational. So t minus 5 times, 5t squared minus 38t minus 120 equals 0. The inquisitive, the curious part of me is really trying to want to factor this as a whole. Maybe I can do some of it mentally with factors of 120. I feel like if a number multiplied by 5, though, wouldn't really pan out unless it was something unique. 2 and 6. Well, they go opposite signs. I don't know if it's worth dabbling into. Here's what I'm going to try. I'm going to work off the discriminant here of b squared minus 4ac. If it is a perfect square value, I will instead do the factoring version. I will find which one it factors to. So 38 squared, I'm going to do 38 squared plus 20 times 120. I don't want to mess that up. I think it's 2400, but I don't want to mess that up. Plus 20 times 120 and take the square root of that. It's a perfect square. It's a perfect square of 62. Okay, this is factorable. Okay, guys, I'm going to try and factor this. That's my own doing. I want to try and do it. It is factorable, and therefore we're going to have to play with it. So 5t and t. Now, there are a lot of factors of 120. We have to go to work hard. One's a plus, one's a minus, don't know yet which. This is the part where we get a little dicey. We have to try some things. Like, okay, what are factors of 120? I should probably list them out. 120 and 1, 60 and 2. I'm going to go with it until I see it. I will see it eventually. 40 and 3. 30 and 4. What and 5? 24 and 5. 20 and 6. Nothing in 7. 8 and 15 and 8. I'm trying to test in my head and see if those work. Oh, it was the easy one. It was the easy one. It has 10 and 12 and 10. 12 and 10. 12 and 10. This is negative 50 plus 12. I should always go for the closer ones, which is negative 38. Okay, there it is. So it is factorable. Those are our solutions. 5, negative 12 fifths, and 10. Now, when it comes to time, this is time in years. Negative values won't apply for the 10-year period. They say during a 10-year period, so far 5 and 10 still apply. That being said, for part A, I wrote the equation. Hold on. I've kind of done a lot of this already. I think I solved before I was supposed to. Part A would have gotten me to about, say, right there. I did some factoring. Part B says list the possible whole number solutions of the equations. Consider the domain when making your list of possible solutions. I didn't consider my domain, but guess what? I went all the way to 10 and I stopped. So there it is. I actually really lucked out on that. I didn't even realize that. And then part C, use synthetic division to find when it's sold. I actually started that here. So I got to this thing here. My answers are 5 and 10. Do both work? I mean, when it comes to my graph, I guess that's 10. I didn't realize that. When it comes to my graph, they both hit 0. Does 10 count as a part of the 10-year period? What does it say? Write a polynomial equation to find the year when about this much athletic equipment is sold. Can it be two different ones, or would it say that the other one doesn't count? I'd say 5 is the one that does count, and maybe 10 is the one that doesn't. Maybe 10 is not within its own 10-year period, if that makes sense. So I don't really know when it comes to that. I'm going to say 5. So 5 years. I'd say the problem with the 10 is it's right on the cusp. It says during a 10-year period, and maybe 10 itself doesn't actually count as one of those things as a whole, right? And that's where I'm kind of at a loss of being able to decide that. You know what? It says during 10-year period. 10. They said list 10 as your rational solutions. I'm going to do both of them. 5 years, 10 years. I think those should both be fine. Okay. Really, truly at odds with myself, as you can tell. Okay. Oh, you can't see anything that I'm writing. I apologize. I thought that you were looking at this screen. I just wrote the 5 years and 10 years. I hate when I do that. All right. That is... Did you get to see all that I wrote over here? Did you see me box all this? Oh, shoot. I hope you saw all this, too. Ooh. I can't tell. I can't replay my video. Okay. I hope that you saw that I said that this was the true list of possible values. Now I don't know, so I have to go back. This is the true list of possible values that we could write within 10 years. This was part A, B, and C. Oh, I hope you saw that. I hate making mistakes like that. All right, number 54. Number 54. Write a third or fourth degree polynomial function that has zeros at, I assume that's supposed to say plus or minus 3/4. Justify your answer. All right, well, this is open-ended. They said third or fourth degree, so it's really up to us. So x equals plus or minus 3/4 really means x equals, excuse me, if I multiply both sides by 4, that would say 4x equals plus or minus 3, and that's big for us. So 4x equals 3, 4x equals negative 3. When you subtract those over, 4x minus 3 equals 0, 4x plus 3 equals 0. So as far as our factorization goes, and they said third or fourth degree, you can make up whatever you want for the other one. I'm going to make it easy. I'm going to make the other one x. X times 4x minus 3 times 4x plus 3. So this has zeros at 3 and 4. Oh, you know what? I think they mean they don't want any other zeros. So let me get rid of that one. So let's do this. 4x minus 3 times 4x plus 3. But the problem with this is, of course, this is only 2. This is only degree 2. So what you'd have to do, this is why they're saying third or fourth degree. They're saying, hey, what if I take one of these and square it? That would work out. That would be fine. You might think, hey, if I just square one of them, that would be easier than squaring both of them. I actually think it'd be easier to square both of them, and here's why. If you square both of them, that means that there are 2 instances of these. We can do 4x minus 3 times 4x plus 3 twice. And if you do that, those are differences of 2 squares. I can do this times this, 4x minus 3 times 4x plus 3, or 4x, or 4x minus 3 times 4x plus 3 is 16x squared minus 9. It's the difference of 2 squares. Because there are 2 of them, we can square that result. Now, you'd want to write it in standard form, so a perfect square trinomial for this thing will be 256x to the 4th minus, we got a double 9 times 16, double 144 is 288, and I wrote a 4 for some reason, minus 288x squared plus 9 squared, 81. So there's a 4th degree version of that with a leading coefficient of 1. If I just squared one of them, I'd have a cubic. I'd probably have some more expanding to do by common distribution practices, but this used difference of 2 squares and perfect square trinomial. So I kind of preferred that method. That was my go-to. Justify? No, I'm good. I mean, I did it. I used the math. Number 55, modeling with mathematics. You're designing a marble basin that will hold a fountain for a city park. The sides and bottom of the basin should be 1 foot thick. Designing a marble basin. The sides and bottom of the basin should be 1 foot thick. Its outer length should be twice its outer width. They have that written. And outer height. What should the outer dimensions of the basin be if it is to hold 36 cubic feet of water? Okay. If the drawing makes sense to you, because I think it makes sense to me and I don't want to mess up what this is, but if this makes sense to you, they said the bottom is 1 foot thick as well, I believe, right? So this is 55. What I have is an inner portion that's like right here. Hopefully you can kind of see there's an inner wall like that. And it would go, I guess, to there. But this is all 1 foot above that right there. So this is kind of like 1 foot in these. Oh, man. I have no way of drawing this to really make best sense of it. But this is the inside that fills up with water right there. Whereas this goes 1 foot over here and over here and over here and even down there. Those are all 1 foot, things like that. So the inner portion, you know, the part that can hold 36 is taking the dimensions, the 2x, x, and x, and subtracting 1 from each side of them. Well, not the height, but the base, the water basin thing, the volume, we're going to do the length where we have to take away 1 from here and 1 from here, so 2x minus 2, times the width, which is x, but you got to now take away a 1 from here and a 1 from here, so minus 2, times the height, which is x, but we only take away 1 from the bottom, not from the top, because there's just a kind of hollow top there. So I believe this would be the volume, and this equals 36 cubic feet of water. That's what we're going to use as far as solving goes. Now, I'm going to factor out this 2. I got an x minus 1 when you factor out the 2, because there's another x minus 1. I can square that, and I got x minus 2 here, and that equals 36. I can divide these by 2, turn this into 18. Meanwhile, I can expand all this. This x minus 2 will multiply by x squared minus 2x plus 1. That's the expansion of x minus 1 quantity squared. So I'm working out some math things to make it easier looks for me. I definitely want to make them better like that. Now, this is x cubed minus 2x squared plus x minus 2x squared plus 4x minus 2 equals 18. Let's subtract the 18 over while combining like terms in here. X cubed minus 4x squared plus 5x minus 20 equals 0. And that's our setup. Now this, as I look at it, is factorable by grouping. This is factorable by grouping, which is good. I factor out x squared negative x minus 4 plus 5 times x minus 4 equals 0. I got the same x minus 4s. That's what makes it factorable by grouping. X squared plus 5 and x minus 4 are here equals 0. X squared plus 5 will lead to no real solution, so I'm going to leave it for the sake of word problems. x equals 4 is the only thing that we care about. What should the outer dimensions of the basin be if it is to hold 36 cubic feet of water? We need 2 times 4 and 4 and 4. So the dimensions are going to be 8 feet by 4 feet by 4 feet. So that should be the final answer of that based on the knowledge of the problem that we have constructed on 55. There. All right, number 56. How do you see it? I think we have 10 questions left. How do you see it? Use the information in the graph to answer the questions. I see possibly an even degree with a positive leading coefficient. I got multiplicities on those intercepts. So number 56, what are the real zeros of the function f? The real zeros are -2 and 1. They each have multiplicities of 2. Let's see if they talk about it. Write an equation of the quartic function in factored form. Yes. Because x minus 2 is one of the zeros, x plus 2 is the factor. I don't know what I said. If I said x minus 2, I meant because x equals -2 is one of the zeros. Because x equals 1 is one of the zeros, then x minus 1 is a factor. However, and I didn't actually need room in front here. However, these should be squared. Because of the multiplicities of 2, they're even mentioning it's a quartic function, these should be squared. This is what we're looking at for this problem here. Let me give it some more space. They said leave it in factored form. Factored form it is. We're done. Multiplicities of 2 because of the bounce off of this. And by the way, although I don't want to expand this in standard form, if you plugged in 0 into here, 0 plus 2 squared is 4. -1 squared is 1. 4 times 1 is 4. When you plug in 0, you get the y-intercept. Your y-intercept is 4. This is in agreement with it. It is possible that this could have been like 8, and we would have had to have doubled everything. I didn't look at that to start with, but it looks like this is going to be it. Number 56. Number 57, reasoning. Determine the value of k for each equation so the given x value is a solution. All right. We've done things like this before, but I don't know if these will be different than the ones we did before. A lot of ways you can go about this, whether you want to use synthetic division or plug in the numbers. You can just literally plug in 4. So let's do them different ways in different problems. Let's plug in 4 this time. So we got 4 cubed minus 6 times 16 minus 28 plus k. Combine these. 64 minus 96 negative 32 minus 28 is negative 60. So if I did that right, k equals 60. It's number 57, or that's part A on number 57. On the next one, I suppose I'll use synthetic division on it. If y'all don't mind, I'll kind of just swap them. So part B, and then I'll decide which one seems to be best for the last problem of it. Part B, we have 2x cubed plus 7x squared minus kx minus 18 equals 0. So the second option here is use -6 as your root. Use this. Like I said, we've done problems like this before in such a way that we solve for k. And work this out. Now here these add to become 30 minus k, and then distribute the -6, and that becomes positive 6k minus 180. Combine those, that's 6k minus 196. We got to set this equal to 0. I might have done a number wrong with there because I feel like this is that going to be an integer? I don't think that's an integer. Let me 198. 198. I was thinking like I don't want a fraction right now. I want to trust that they're going to give us integer values. So 6k equals positive 198, excuse me. 6k is 198 divided by 6k equals 33. So I'm going to trust that more, especially now that I added those correctly. Depends on the numbers. I kind of liked the first one a little bit more. I think that one required more for us to figure out. Although these numbers are pretty big, part C. Maybe I will use synthetic division one more time. So 57 part C. We have k x cubed. You know what, though? The problem with synthetic division on this one is your k is going to carry to each part of the equation when you do it, because k is the leading coefficient on this one. We'll try it. We'll see how busy it gets, if it's a problem or not, or if it's just, if it's 2 in the way. All right, bring the k down, multiply by 5, and then this adds to 5k minus 35, and then you distribute. Oh, this is going to be big no matter what you do. Minus 175, and that's 25k minus, oh, now I'm going to have to use the calculator after this part, minus 156, and then that's 125k minus, I got this, 780? Oh, okay. Well, anyway, if this is not an integer, then I'm not going to trust it after. Minus 750 when you add those. So 125k minus 750 equals 0. Add 750 to both sides and divide both sides by 125. That works. Isn't that 6? K equals 6. So I'm going to trust my own numbers with that, given that that's there. It seems pretty good. At least they're integers. So looks good. Yeah, I don't know if synthetic division would have been better than the other. Obviously, you can use a calculator either way, but there it is. Now they think about it, the other one probably would have been better. Number 58. Number 58, writing equations. Write a polynomial function g of least degree that has rational coefficients, a leading coefficient of 1, and the zeros -2 plus root 7 and 3 plus root 2. Okay, I'm probably going to use the version that I've been doing previously with these, like for myself, as far as before getting in factored form, kind of writing the versions of expanding this out. Remember, this would need a plus or minus root 7 and a plus or minus root 2. That means if x equals -2 plus or minus root 7, I can add 2 to both sides to isolate the radical, even in that form, and then square it. And when I square it, this kind of cleans things up for me better. X squared plus 4x plus 4 equals 7. Subtract the 7 over x squared plus 4x minus 3 equals 0. So this is one of my factors right here. My other factor is right here. If x equals 3 plus or minus root 2, subtract the 3 over, and then square both sides. When you square both sides here, this expands to x squared minus 6x plus 9, and that equals 2. Subtract the 2 over, you get x squared minus 6x plus 7 equals 0. So, because they said least degree here, so f of x equals, now we got to multiply these, x squared plus 4x minus 3 times x squared minus 6x plus 7. Let's go to work. We got a 3 by 3. Maybe on the 3 by 3, yeah, I'll do it in one line. All right, x squared times these. X to the 4th minus 6x cubed plus 7x squared. 4x times these. 4x cubed minus 24x squared plus 28x. Negative 3. Running out of room. Negative 3x squared plus 18x minus 21. I was thinking of doing the box method, and I probably should have. All right, f of x equals, I got an x to the 4th. I got negative 6x cubed plus 4x cubed. 7x squared minus 24x squared is negative 17x squared. Minus 3x squared is negative 20x squared. 28x plus 18x. And minus 21. So that is of least degree. Let me make sure all the instructions are right. That is of least degree. That has coefficient hold on a second. Is that right? 28x. I'm questioning that x there when I'm looking at it. I have plus 18x. Let me make sure that was right. Let me double check it. Okay, all seems good to me. I want to make sure. I thought I should have an odd number, but it seems like it should be even. Okay, so anyway, leading coefficients 1. We have least degree, all that stuff, all rational coefficients. Looks good. All right, numbers 59 to 62. Solve f of x equals g of x by graphing and algebraic methods. So they're saying both? Oh boy. They want a lot out of these problems here. I'm going to start with algebraic methods. We'll get to the graphs after. Well, the graphs might be a part of what we do here. I'll start algebraically. All right, so with this first one, when you set them equal, you get x cubed plus x squared minus x minus 1 equals negative x plus 1. We get to add the x and subtract the 1 over. Adding the x cancels the x's, but subtracting the 1 gets you actually negative 2, like that. we have to solve that using, well, I guess rational root theorem. Now your p's over q's are just plus or minus 1 plus or minus 2. You can test 1. 1 plus 1 minus 2 is 0, so 1 works. F of 1 does equal 0. So we're going to use that in synthetic division with a 1x cubed, 1x squared, 0x, and negative 2. We get 1, 1, 2, 2, 2, 2, 0. So this becomes x, let's see how I say this. This becomes x minus 1 times x squared plus 2x plus 2 equals 0. So that's not factorable. I can solve by completing the square if I'd like to, but x equals 1 is a solution we already found. X squared plus 2x plus 2 equals 0. If I use completing the square here, I get x squared plus 2x plus 1 equals negative 2 plus 1. So, wait, what do they want? Solve by graphing? So this is going to have non-real solutions, which to us just means no real solution. It doesn't mean that we couldn't keep going. Well, it did say solve algebraically. So here, I'll give you the solutions. But when they say solve by graphing, there's only one place it's going to intersect, and that's at 1. Anyway, so, and I don't know if they want the system, like what the y value is. I don't think so. But okay, x plus 1 equals plus or minus I. Come on, x plus 1 equals plus or minus I. See, the reason why I don't think we're supposed to do this is we haven't really been talking about this. Negative 1 plus or minus I. Now, solving by graphing means we now got to graph these two things here. Let's, we got to get into the whole factoring and all that kind of stuff. I got to bring it down here, see if I even have any room. So with this number 59, one more time, they should only intersect at x equals 1. And the real problem with me and intersecting on that is, well, how do I say it? I don't scale these graphs. So with this one here, we should know how to graph that, but this guy's going to take a little bit more work because with this guy here, we can factor it by grouping. These are going to be long problems, guys. X squared times x plus 1 minus, factor out a negative 1, we get x plus 1. So this factors into x squared minus 1 times x plus 1. X squared minus 1 is x minus 1 times x plus 1. And because there's already an x plus 1 there that multiplies by it, that means we can make that squared. So we get x-intercepts of 1 and negative 1. This is going to have to go down a little bit, sorry. Of 1 and negative 1. The negative 1 has a multiplicity of 2, so I'll put just times 2 there. The leading coefficient is positive. The degree is odd. It'll start down, finish up. The y-intercept is negative 1. So as far as a graph goes, let me get graph paper on this one. This is just but one problem that we've started, and it's probably the easiest of them. So this is quite a bit of work on these ones. As far as the graph goes, let's start with g of x so I can make sure that this just intersects at x equals 1 appropriately. Oh, I think they're actually going to cross at the x-axis, so this is fine. All right, g of x, negative x plus 1 is a y-intercept of 1 and a slope of negative 1. So it goes like this. Boom, 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 boom. And then upwards, boom, 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 boom. Yeah, I was fine solving algebraically first. Looks like this part's even a little bit harder. Or longer to do. So there's g of x. F of x is... we have intercepts at 1 and negative 1, so clearly that 1 means that's where it hit, negative 1. And it has a y-intercept of negative 1, and it starts down, finishes up. So it's going to start from the bottom, come from down here. It's actually going to cross, wait a second. Oh, negative 1 was its multiplicity of 2. Okay, it's going to bounce off of negative 1 here, go through there at some point, I guess like that, and just bounce up there and go through. So this shows that these two intersect at x equals 1. That is solving by graphing on that one. Maybe they wanted you to use, graphing calculator. I think in that particular instance, it seemed right to do that, even though it took a while. I don't know how much room I have on my computer for this for the rest of the way. Let's see. We're running pretty short here. Number 60. Let's see if we can get there. Number 60. F of x equals x to the fourth minus 5x cubed plus 2x squared plus 8x, and g of x equals negative x squared plus 6x minus 8. Not only is this harder, I ran out of room already. So I'll write it like that. All right. Yeah, these are going to take a while to graph, guys. Let's begin by solving algebraically. X to the fourth minus 5x cubed. Let's just hope they're always integers. You know, even those non-real solutions, I don't know if it panned out for me to do that. Add x squared, subtract 6x, add 8. So x to the fourth minus 5x cubed. Add x squared, subtract 6x, add 8. No common factors, no factoring by grouping available. We have p's over q's of plus or minus 1, 2, 4, and 8. We'll try and plug in numbers till they work. Plug in 1, looks like no dice. Negative 1, we get 1, plus 5 is 6. That doesn't work. All right, I'm going to put this in my calculator just until we can find that actual number here. So we're going to have x to the fourth minus 5x cubed plus 3x squared. This, you could solve this by graphing on the calculator. Plus 2x plus 8. Let's see. Plus or minus 1, I don't think works. Try 2. All right, 2 works. Okay. So with 2, f of 2 equals 0. Therefore, we're going to, sorry if you're getting blindness from that. Let's maybe turn these blue. All right, so using synthetic division with 2, we're going to have 1, negative 5, 3, 2, and 8. Sorry if those aren't, I'm apologizing too much. I'm sorry. Those aren't very spaced out. All right, so we get that. Now here's the problem. This is only a cubic at this point. That means there's still more to solve. So this factors into x minus 2 times this x cubed minus 3x squared minus 3x minus 4. Unfortunately, that still isn't factorable by grouping. Now, my curiosity is, does 2 work again? You always want to think about that. We get 8 minus, I don't think that's going to work. So we'll keep trying some more ones. The ones that didn't work before can't work now. The only possibilities now, however, are plus or minus 1, 2, and 4, because now that's what we have there. So we got to see what else works. So let's try possibly negative 2. Nope. 4. Yup. So now we're going to use it with that one. So here we go. We have f of 4 equals 0. And now we do synthetic division on that with this guy right here. Okay, so this guy, synthetic division with 4, we get 1, negative 3, and negative 4. That's 1, 4, 1, 4, 1, 4, 0. All right, now we're stuck with this guy here. So this, we originally had x minus 2. Now we have x minus 4. And then we have x squared plus x plus 1 equals 0. Not factorable, and quadratic formula would probably be the way to go from this. So b squared minus 4ac equals 1 minus 4, which is negative 3. That means no real solutions. Again, I don't know if they want you to actually solve algebraically, but I will because it doesn't take too long. I root 3 over 2. It's negative b plus or minus square root of b squared minus 4ac over 2a. These ones otherwise are x equals 2 or x equals 4. So we have two different places where these graphs cross. And that kind of makes sense given the nature of the functions, especially because one of them is actually a, what do you call this? A parabola, a quadratic. So let's copy and paste that guy. I need to bring it henceforth and do the graph. I think I'm going to do a page, a problem, if they're going to be like this. Let's start with that quadratic as far as graphing, and then we'll go to the other one afterward. I hope that this smaller graph will be enough for it. I cannot guarantee that at all. So negative x squared plus 6x minus 8. I actually can do some groundwork on that one too. This one, let's get into vertex form. Well, let's factor. Negative x squared minus 6x plus 8, which is x minus 2 times x minus 4. So your x-intercepts for this one are 2 and 4. Isn't that where they cross together? Isn't that where they meet? Anyway, so 2 and 4 for that one. You plug in the vertex of 3. 3 minus 2 times 3 minus 4. Opposite of that is negative 1. It goes, or is 1. It goes right there. And you got a stretch factor of -1. So 1, 1, 2, 4, 3, 9. And that graph does have a -8 y-intercept, so that does make sense that it goes down right there. Here's the parabola of this guy. Now the other one, we still have to do some work and find out what its x-intercepts are. We know it has a x and y-intercept of 0 somewhere because this common factor of x, let's take care of that first. X cubed minus 5x squared plus 2x plus 8. We cannot factor by grouping, so we have to test some values here. -1 actually works. I'm trying this out. -1 minus 5 is -6, minus 2 is -8, plus 8 is 0. So let's use synthetic division with -1. Sorry, I'm really pressed for time because of space on my computer. I feel like I'm going to run out before we finish this as a whole. So I got 1, -5, 2, and 8 here. So it's 1, -1, -6, 6, 8, -8, and 0. That's x squared minus 6x plus 8 as well. And we saw how that factored. So this factors into x plus 1 times x squared minus 6x plus 8 is x minus 2 times x minus 4. So therefore it has those solutions of -1, 2, and 4. Those are x-intercepts. We also had an x-intercept of 0 because the x that's there. So 0, -1, 2, and 4. It does not have any multiplicities anywhere. It is positive, so it's going to start from the top. Oops, it's going to start from the top. It's going to go down and through, go up and through, come back down and through, come back up and through, like that. And that's where they intersect like that together. So there's the solution by graphing those two. All right, and that was a whole page length. So let's hope they get a little easier. Number 61. Number 61, sorry, again, it's a rush at this point, guys. I'm going to do blue and green just so I already have them straight up set. X cubed minus 4x squared plus 4x. And then G is -2x plus 4. We already know that one's graphed, but let's start with the solving. X cubed minus 4x squared plus 4x equals -2x plus 4. And I don't even know how the last problems go after these ones. I still have 2 more after that, or 3 more after that. Ooh, my time is a factor. Add 2x, subtract 4, not factorable by grouping. What else is new? Factors of this, though, are 1, -1, 2, -2, 4, -4. If you plug in 1, it doesn't work. -1, it doesn't work. 2 cubed, minus 16 is plus 6, right? Did that work? I think that worked. I think 2. I'm going to try 2. I believe that worked in my head. 6 and -4. Here we go. 1, 2. Yes. All right, 2 worked. So this factors into x minus 2 times x squared minus 2x plus 2. And we already saw an instance of that, but x equals 2 is the main. As far as solving imaginary solutions, minus 2x plus 1 equals -2 plus 1. That's completing the squares, what I'm going after here. X minus 1 squared, and sorry, I'm not spending time really explaining this one for a couple reasons. 1 time. 2, I don't know if you have to do this part. 3, I don't know if that'd be quite enriching for you to do that. So 1 plus or minus I, but they don't cross there together. But we are going to go ahead and graph these two now. I think I'm going to have to clear some computer space after this problem. I'm really, once I hit that 4-hour mark-ish is when it's kind of going to be time's up. And these problems, as you can tell, go really long. So f of x is a common factor. And that is a perfect square trinomial, which is x minus 2 quantity squared. So your x-intercepts of this guy are 0 and 2. That has a multiplicity of 2, by the way. And it's a positive cubic function. The y-intercept is 0. So let's graph it against that g of x equation, -2x plus 4. So let's start with the blue. The blue one, we have 0 and 2. We have positive cubic, so it's going to start from the bottom and come back up. It'll bounce off of 2. So it's going to go through here. It's going to bounce off of 2 when it comes back down and finish up like that. Not a beautiful looking graph. The other one's negative 2x plus 4. So y-intercept of 4 and a slope of negative 2 like this. And we go, and we go, and we go. And it goes through right there, and you can see that they cross together there. Now, they seem to... Okay, now my graph actually does matter how I draw it, because now it's crossing multiple places, right? So what's important for here is it doesn't cross multiple places. So, because that's the official scaling of that graph. So this graph must do a lot less when it comes to that curve. So I'll make it kind of come through like that. And it's going to... Whoopsie. It's going to come back down and through, hit off that, and go back up. I can't have it hit more than once. That's the only time we can hit at x equals 2. Okay, last one of these sets, we have quite big values. Who knows if that makes it hard or not? Let's go to number 62. And then I really will have to check on computer space. So f of x equals x to the... Whoops, I didn't change the color. X to the 4th plus 2x cubed minus 11x squared minus 12x plus 36. And g of x equals negative x squared minus 6x plus 9. Oh, minus 9. All right, let's set them equal to each other. I keep on writing a plus after that. I'm thinking of minus 6x plus 9 like the perfect square trinomial, and it's not it. Add x squared over. This is probably easily the hardest of the problems. Add 6x over. Add 9 over. Not factorable by grouping, so we have factors of 45 to consider. I'm going straight to my calculator for that. Let me pause. Now time is a problem. Okay, so I entered it in right here. We're going to test numbers. Let's see, 1, negative 1, 2. Oh, 45. 2 is not a factor of 45. 3 and negative 3. Negative 3 works. Okay. So with negative 3, we're going to try that out on synthetic division and break it down. Hopefully the cubic after that doesn't require another set. Maybe we can factor by grouping. Maybe it's some sort of special case thing. Let's see. Negative 3 is negative 1. 3 here is negative 7. Probably not. 21 is negative, or is positive 15. And then negative 45 and 0. Yeah, definitely not. So this one now breaks down to x plus 3 times x cubed minus x squared minus 7x plus 15. Not factorable by grouping. Now, I will need to test this one with it. So let me put that one in the calculator as well. Give me a second. So this one here, now typed in, we have more tests to do. Remember, tests that didn't work before would work now. I just pop this up. We still get another 0, which means negative 3 works again. That's another multiplicity of 2. So, or that it is a multiplicity of 2. So with this one, we use synthetic division with the negative 3 again. I did state that it could happen more than once, and here's a case where it does. Those were just the same entries as before, so you always retry your entry again. I'd always recommend that. So negative 4, 12, 5, negative 15, and 0. That one doesn't have good solutions there. So x plus 3 squared times x squared minus 4x plus 5. Now that's still not factorable for that guy. Now x equals negative 3 is a solution. It has a multiplicity of 2. I don't really know what that means when it comes to, I guess it must bounce off of the linear equal. Well, the other one's not linear. So we'll see what that one looks like. This is x squared minus 4x plus 4 equals negative 5 plus 4. These are the imaginaries. X minus 2 squared equals negative 1. X minus 2 equals plus or minus I. So x is 2 plus or minus I. That's the algebraic solution. So negative 3 is really the only time that it's going to cross, but I guess it's going to probably bounce off of the other graph. So we have to now graph them. Let me get this copied and pasted down below. Figure out how to work these ones out in a way that's helpful for us. So in blue will be this, and green will be this. Let's start by working out the green g of x. We can factor out a negative 1, and we get x squared plus 6x plus 9, which actually happens to be, oh, this is cool, x plus 3 quantity squared. So this is also vertex form, if you will. If you know what vertex form is all about, it is Your HK is negative 3 comma 0. It's got a stretch factor of negative 1. So this will be a nice quick one for me to be able to graph on this. My vertex, negative 3, 0. Stretch factor, negative 1, 1, 1, 2, 4, 3, 9. It did have a y-intercept of negative 9, so that agrees. And our curve is going to look like that. Now the next one, I can only imagine that x equals 3 is one of the solutions on blue. Let's do some of the work with that one. I got to test some p's over q's with this guy right here. So factors of 36. Why don't I just say negative 3 is going to be one of them, right? It has to be, considering my solution. So I tested some numbers out. Negative 3 works. So here we go. We try negative 3 on this thing, and we have 1, 2, negative 11, negative 12, and 36. So as we work that out, okay, that worked out, right? Although we're still not done with that. Okay, we still have more to do, and I'm out of space on there. So this becomes x plus 3 times x cubed minus x squared minus 8x plus 12 for the function. Setting equal to 0. Well, this is a graph. Well, yeah, set equals 0. We've got to find x-intercepts, right? So can this plug in negative 3? This is the point where I probably got to use the calculator. Hold, please. Okay, so in the calculator and typing this in, let's see. Negative 3 still works. So it's one of those multiplicities of 2, right? That was kind of what we anticipated. So as we go back here, we got to use synthetic division another time with negative 3 on this part. 1, negative 1, negative 8, 12. I was hoping these parts would have been a lot faster. These are probably the longest problems of the bunch. And that's x squared minus 4x plus 4, which happens to be real solutions there. I mean, these are part of the graphing, right? So this is x plus 3 squared times x squared minus 4x plus 4 equals 0. And that factors, oh well, out of space, x plus 3 squared times x minus 2 squared. So your x-intercepts are negative 3 and 2. Each of them have a multiplicity of 2. Each of them have a multiplicity of 2. So let's go and plot those ones. Negative 3, and 2. This also had a y-intercept of 36. Now, I'm not truly going to be able to fit that. It just goes up somewhere. And it's a positive even degree function. But it's going to go in this direction here. Notice the bounce off. And then it does something. It hits 36. Oh, well. We won't actually be able to fit that one. And it goes like that. And you can see that they only actually cross here. And there's that multiplicity of 2 thing that they also kind of mentioned, which is interesting how that comes to be with that. So there's x equals 3. All right, I'm going to pause, see if I can clear some space out for the last 3 problems. Okay, I tried to clear up a few gigabytes of space. Let's see if we can now go the distance here. Let's give it a shot. Number 63, modeling with mathematics. You're building a pair of ramps for a loading platform. The left ramp is twice as long as the right ramp. Okay, I see the ramps. Whoa. If 150 cubic feet of concrete are used to build the ramps, what are the dimensions of each ramp? So those are triangular prisms. I probably should have looked at the problem before we started. So x is the height, 21x plus 6 is the whole thing. You subtract 3x from there. So let's see. I'm just going to kind of work out some things. 21x plus 6 minus 3x gives you the width of both ramps combined. That gives you 18x plus 6. So that's both ramps. The left ramp is twice as long as the right ramp. So let's see. So 18x plus 6, if I divide it by 3, if I multiply by 2/3, then I get the length of one of them. If I get the times 1/3, I get the other, right? So times 1/3. So divided by 3 clearly would be what? 6x plus 2, and then times that by 2 is 12x plus 4. So these are both ramp lengths. The heights are x, the widths are 3x this way. So the volume, 150 cubic feet. So the volume is 150. If I set 150 equal to, now one's twice as large as the other. Clearly I could just do 2 times that, but let's just make sure that we write it in a way that'll make sense to us. Actually, no, you know what? Yeah, I don't need to split them up like this. I think at all. They're both the same length. They're both the same width and height, so I actually don't even need to do this part. Let's just keep all of 18x plus 6 intact. That's all I care about. Both lengths together. Oh, wait a second. Maybe. These are base areas. You know what? Let me go back. That's fine. So the volumes here, I have area of base is 1/2. For this one, base times height, and then times the height of the prism, plus the other one is 1/2. Yeah, I think this would have been the same either way. Base times height times the thing of the prism. You're going to have to know how these volumes work by triangular prism standards. It's something we did at the time. So let's see. This would be 1/2 of 12x plus 4 is 6x plus 2. We're going to have to multiply that by 3x squared. And then same with this other one. Half of that is going to be 3x plus 1. And multiply that by 3x squared. Yeah, that would have been faster to do the other thing. Equals 150. So this becomes 18x cubed plus 6x squared plus 9x cubed plus 3x squared equals 150. Or 27x cubed plus 9x squared equals 150. I can divide all of these by 3 and get 9x cubed plus 3x squared equals 50. And I can subtract the 50 over to begin trying to solve this. Now, this is one of those ones where I'm going to write it in my calculator. I'm going to find p's over q's, factors of 50 over factors of 9, and see what works. Hopefully an integer one works. Okay, so for time's sake, I did two things here. First thing I did was I put this in, and I started testing numbers. Now, no integers actually worked. I went to here. I didn't type these decimals. I typed 1/3, -1/3, 2/3, -2/3, and 5/3. So the integers didn't work. I had to go to fractions, factors of 50 over factors of 9. 3 is among them. So 5/3, factor of 50 over factor, that one worked. So you plug in 5/3, it works. So we're going to use synthetic division on that one. So we have to try 5/3 with, or you can use long division, with 9, 3, 0, and -50. And here we're going to get 5/3 of 9 is 15. That's 18. 5/3 of 18 is 30. And 5/3 of 30 is 50. So now with 5/3 there, I'm assuming that's going to be the only like one, right? If some other ones didn't work, but x minus 5/3 times I got 9x squared plus 18, whoopsie, x plus 30. And keep in mind that you can factor a 3 out of these and pour it into here. So you get, 3x minus 5, and this now becomes 3x squared plus 6x plus 10. And if I do that one in my head a little bit, factors of 10, 2, 10, 1, 2, 5, those have no real solution. So the only actual solution here is going to be x equals 5/3. Now they asked what are the dimensions of the ramp. So as far as, wait, what was the question? What are the dimensions of each ramp? So long ramp, I guess this is where you had to separate the things. So long ramp, you have, let's see, how do they call it? Length is going to be 5/3. 8, what is it? 12 times 5/3 plus 4, which is 4 times 24 feet. The width, I don't know what they call them. The twice as long as the ramp. I'll call it the width, which is the 3, I guess. 3 times 5/3 is 5 feet, and the height is 5/3 feet. Now, the short ramp has the same dimensions for the bottom, for the width and height, but the length is just going to be half of that, so 12 feet for that. So if I copy and paste this, I will actually get the same. Did that work? Nope. If I copy and paste this, I will get the same, come on, there it goes. Get the same answers everywhere else, except this will be a 12 instead of a 24. So that's how those should work out. Okay, number 64. Some ice sculptures are made by filling a mold and then freezing it. You're making an ice mold for a school dance. It's said to be, or it is to be shaped like a pyramid with a height 1 foot greater. They already got it listed. Then the length of each side of its square base. The volume of the ice sculpture is 4 cubic feet. What are the dimensions of the mold? So the setup for the, whoa. Oh, I ran out of binder paper. I've done this before. Let me pause and get myself more binder paper. All right, we're back. Okay, so the number 64, we got to find this volume. volume being 4 equals 1/3 area of base x times height, x plus 1. I'm going to multiply everything by 3, make it easier for myself, and distribute the x squared into here to get x cubed plus x squared. So now we have x cubed plus x squared minus 12 equals 0. Once again, for me, 2 works. 2 works. 2 cubed, 8 plus, yep. So instead of using the calculator there, 1, 1, 0, negative 12 is our synthetic division process on this to break it down to something else. We get 1, 2, 3, not 4, 6, 12, and 0. That is x squared plus 3x plus 6. Clearly not factorable. No real solutions on this, but the x minus 2 times x squared plus 3x plus 6 equals 0. No real solutions on this guy. This is just going to be x equals 2 for that portion of the answer. They said, what are the dimensions of the mold? The dimensions are a base of 2 feet by 2 feet by 3 feet. And that would give you area of base of 4 times height of 3, and 1/3 of 12 is 4, so that works out. All right, the last question, number 65, abstract reasoning. I'm still pressed for time, despite my clearing space. Let's see. That problem, I think I have enough time. I can work this out. Number 65, it depends on the length of the problem. Let a sub n be the leading coefficient of a polynomial function f, and a sub 0 be the constant term. If a sub n has r factors and a sub 0 has s factors, what is the greatest number of possible rational zeros of f that can be generated by the rational zero theorem? Explain your reasoning. So this one here, it sounds all weird, but consider what we've done for previous problems, right? If I had p's over q's be, say, factors of 10 over factors of, like, say, 4 or something like that. Well, not 4. Let me do, like, 3. Like 10 and 3, right? The factors of 10, there are, so plus or minus, right? But there's just 1, 2, 5, and 10. That's 4 of them. And then for 3, it's 1 and 3. So the idea behind that is you do these divided by 1, and then these divided by 3. That's 8 of them, and you double that amount, right? Because the plus or minus. So you just multiply however many factors there are of each, and then you double it, I believe. So the p's over q's equals, there are r factors. A sub n has r factors. That's the bottom thing, whatever. And as s factors. So r times s would be that thing. And I think you can double it because when it comes to the plus or minus aspect of it, possible factors or rational zeros to list. Now they said explain your reasoning. This is because you can possibly divide each number on top by each number on bottom, making that total amount a product of the number of items on top and bottom. And you would have to double it to consider all plus or minus possibilities. So it's all the positives and all the negatives. That's why there's a doubling effect that's going on there. So I believe that that's what that would work out to be. I'm trying to think if there's a reason why it wouldn't be that. But they did state each factor. Yeah, so that's what I'm going to go with. So 2 times r times s, assuming you're doing all the pluses and minuses there. Okay. Let me make sure. Leading coefficient polynomial function, that r factors. Yep. Okay. All right, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. That was very long. Yeah, that's it. Take care. See you in the next one.